In this lesson, we want to talk about polynomial functions and their graphs. All right, before we jump into the lesson, let's just go over a few basic definitions. These are things we're going to refer to constantly in this lesson. So if we have something like this right here, it represents a polynomial function of degree n. So you see here we have that n is a non-negative integer and represents the degree of the polynomial. We are also going to say here that a sub n, so this guy right here, is not allowed to be equal to 0. So just think about this with a simple example. Let's say you have f of x is equal to, let's just do something like a quadratic so it's easy, so 2x squared minus x minus 1. If you think about the degree of the polynomial, what is it? Again, it's the highest exponential power, so it's going to be a 2. So that's all we're saying there. That n right there is representing the degree of the polynomial. And remember, when you have a polynomial, you want to make sure that the exponents on your variables are whole numbers only. You can't have a negative, you can't have a fraction or something like that. So that's why this says n is a non-negative integer, which is basically a whole number. 0, 1, 2, 3, 4, so on and so forth. So let me get rid of this and let's come down here. So we have a sub 0, a sub 1 through a sub n are known as the coefficients of the polynomial. Now, a lot of people get confused about this. So if you have this is the constant term. So we have a sub 0 is known as the constant term or the constant coefficient. So why do you say a coefficient there? What is it the coefficient of? If you had something like, let's say f of x is equal to, let me use another example. So let's go 3x squared minus 2x plus 5. I can legally write this right here as x to the power of 0. Remember, x to the power of 0 is 1, and 1 times 5 is still 5. So that's why you're able to say constant coefficient there. A lot of people just say the constant or the constant term, just so you know that there's different ways to see it, and you might get that in your textbook. So then a sub n, so that's this guy right here, is going to be known as the leading coefficient. So you hear that a lot today. The leading coefficient is the coefficient of the term where x is raised to the highest power. So if the polynomial function is written in standard form, so descending powers of x, it will be the leftmost coefficient. A sub n and then x to the power of n is known as the leading term. So that's going to be this whole thing together. This is the leading term. So the leading term is the term where x is raised to the highest power. Again, if the polynomial function is written in standard form, so descending powers of x, it will be the leftmost term. All right, just to make sure we're all on the same page, we're going to do a quick example. So I have a little table here. We have the polynomial function, the degree, the leading coefficient, the leading term, and then the constant term. So let me go slow for the first one, and then for the next ones, we'll just blow through it. So we have f of x is equal to, you have your negative 6x to the 4th power plus 3x squared minus 2. So this is written in standard form. So basically, when we look at this, the degree, again, you're looking for the highest exponential power. So that's this guy right here. So that's the 4. The leading coefficient is the coefficient for the leading term. So that's going to be this negative 6 right here. Then the leading term, that's the whole thing. So negative 6x to the 4th power. And then the constant term, again, that's going to be this guy out here. So it's going to be negative 2. Now for the rest of them, let me erase this. We'll just go through it really quickly. So we have f of x equals 7x cubed minus 4x squared plus 3x minus 8. So the degree, again, that's just going to be 3. The leading coefficient, that's going to be 7. The leading term, again, that's the whole thing. So it's 7x cubed. And then the constant term, that's the negative 8. Then for this one, f of x equals 9x squared minus x plus 4. The degree is going to be 2. The leading coefficient is going to be the 9. The leading term is going to be the whole thing, so the 9x squared. And then the constant term is the 4. Then for this one right here, we have f of x equals negative 2x minus 5. The degree is 1. Why is the degree 1? Again, if you write this out, so f of x equals negative 2x minus 5, what's the exponent on that x? It's going to be understood to be a 1, so that's why the degree is 1. The leading coefficient is negative 2, then the leading term is the whole thing, so negative 2x, and then the constant term is the negative 5. All right, so at the beginning of this section in your book, they're going to start by talking about transformations of monomials. This is something that we pretty much already know how to do. We studied graphing transformations in great detail already, so I'm just going to run through this and do one example only. So a monomial is a polynomial that consists of just a single term. So something like 5x to the 6th power, or negative 3x cubed, or something like 1/3 x to the 4th power. So each there would be an example of a monomial, because it's a polynomial with one term. Now, just some general information. When we talk about the graph of a polynomial function, so something like f of x equals x to the power of n, where n is even. So we're talking about something like f of x equals x to the 4th power, the 6th power, the 8th power, the 10th power, something like that. We're going to say this has the same general shape as the graph of f of x equals x squared. So we know that's the parabola shape. As the degree of the polynomial n gets larger, the graphs will be more flat around the origin and steeper everywhere else. We can observe this with f of x equals x to the 4th power. So for all of the graphs today, I left you a link for Desmos if you want to view it on your device. Maybe the screen is a little bit hard to see, so you can just pause the video and go to those links. So right here, if we look at this guy and let's call it green, that's your f of x equals x squared. Again, that's our basic parabola. And then we have g of x equals x to the 4th power. So that's the guy in red. You'll notice that this guy right here is flatter around the origin and then steeper everywhere else. Now you can go into that Desmos link that I gave you and you could type in x to the 6th power, x to the 8th power, x to the 10th power, so on and so forth. And you're going to see that it gets more and more flat around the origin as this exponent gets larger and larger and it gets steeper everywhere else. All right, so similar to what we saw above, the graph of a polynomial function f of x equals x to the power of n, where n is odd now, so let me highlight that, has the same general shape as f of x equals x cubed. Again, as the degree of the polynomial n gets larger, the graphs will be more flat around the origin and steeper everywhere else. We can observe this with f of x equals x to the 5th power. So the guy in green is your f of x equals x cubed. We know what that looks like. And our guy in red, that's g of x equals x to the 5th power. Again, you can zoom in on Desmos to make this more apparent, but this guy right here in red, your g of x function, it's flatter around the origin and then it's steeper everywhere else. So if you want to type in x to the 7th power, x to the 9th power, so on and so forth, you'll see that it keeps getting flatter and flatter around the origin and steeper everywhere else. Okay, let's look at an example where we're asked to graph something and it's just a transformation of a basic monomial that we're used to working with. So we have something like f of x equals x cubed. We know what that graph looks like. And then we have g of x equals 1/2 times the quantity x minus 3 cubed plus 1. So we have studied graphing transformations in great detail. This should not be something that you can't do at this point. You know that for the horizontal transformations and the vertical transformations, they do not impact each other, so you can do them in any order. But if you have multiple vertical transformations or multiple horizontal transformations, remember you have to do those in a specific order. So what I'm going to do here is just work left to right. That's going to be fine here. So I'm just going to say the first thing is this 1/2 that's multiplying this guy right here. And again, you can say that that gives me a vertical compression by a factor of 2. I know a lot of people don't like that. They'll say, I want to say vertical shrink by a factor of 1/2. The different terminology there has the same meaning. You're taking the y value and you're either dividing it by 2 or multiplying it by 1/2. So use whatever terminology you want to say. I'm just going to state that there's a vertical compression. So a vertical compression by a factor of 2. Let me fix that. Now, the second thing, I'm going to go inside the parentheses. Now, this is going to impact x here. And remember, with the transformations with x, the horizontal ones, you have to undo what's being done to x. Here we have x minus 3 on the inside. So to undo that, I want to add 3. So that's going to shift me to the right by 3 units. So I'm going to say we're going to shift right by 3 units. Let me fix that. And then when we get back on the outside here, we have this plus 1. Again, that's vertical. So we're going to say that we want to shift up by 1 unit. So just shift up by 1 unit. So it's important that you understand that this one and this one, so the vertical compression, or again, you could say vertical shrink, by a factor of 2, or in the case of vertical shrink, you'd say by a factor of 1/2. This one has to be done first, and then this one would have to be done second. The order of the vertical transformations would matter here because you have 2 of them. But this horizontal one here is not impacted by these, so you could do this in any order. You could do it last, you could do it first, it does not matter. What I taught you in that lesson was you can just work left to right. Again, as long as this part right here was in factored form. Here we don't have anything to factor out. It's very, very simple. We only have one operation in there. We're just shifting to the right by 3 units, so it's not really a big deal. So just keep that in mind. You might need to go back and review that lesson. But I think most of you spent a lot of time on this, so you pretty much can remember the steps that we have here. So if I make a little border here and I say, okay, for f of x, we have some x comma y. Well, then when we go to g of x, what is that going to become? Well, it's going to become your x, all you're going to do is add 3 to it. So it's x plus 3. And then your y, you're going to divide it by 2, or again, multiply it by 1/2, whatever you want to do. And then you're going to add 1 to that. And that's pretty much all it is. Let me go ahead and grab this and come down here. I've already pre-drawn everything for us. So the guy in green, that's your f of x equals x cubed. Again, you should recognize that graph. Your guy in red, that's your g of x equals 0.5 times the quantity x minus 3 cubed, and then plus 1. So thinking about a point like 0, 0, again, where's that going to go to? 0 plus 3 is 3. And then here you'd have 0 over 2, which is 0, plus 1, which is 1. So this 0, 0 is going to go to 3, 1. Then something like, let's say 2, 8, that's going to go to 2 plus 3, that's 5. Let me fix this 3 here. Doesn't look so good. And then this would be 8. So 8 over 2 is 4. 4 plus 1 is 5. So this 2, 8 is going to go to 5, 5. And then the last point we'll do, you can do as many as you want. We have negative 2, negative 8. So that's going to go to negative 2 plus 3, that's going to be positive 1. And then negative 8 over 2, that's negative 4. Negative 4 plus 1, that is negative 3. So this negative 2, negative 8 is going to go to 1, negative 3. So again, with those points, you're able to easily sketch this guy. You know what the general shape is, and you can put more points in if you need to, but I think this is enough to get a good graph going. All right, now let's get into graphing a polynomial function that's not a monomial, so something where we can't just use graphing transformations. And to do that, we need to understand what we're talking about when we say smooth and continuous. So we have smooth and continuous definition. So polynomial functions of degree 2 or more have graphs that are smooth and continuous. When a graph is referred to as being smooth, it means the graph has only smooth, rounded turns. So in other words, the graph of a polynomial function can't have a sharp turn, which is a turn where the direction is changed suddenly. Okay, we're going to talk a lot about this when we get to calculus and we get into derivatives. When a graph is referred to as being continuous, it means the function can be graphed without lifting the pencil from the page. So in other words, there are no breaks or holes in the graph. So let me give you some examples of graphs that are not polynomial functions. So this one right here, if you look at it, you have this sharp turn. You want only smooth, rounded turns. This is a sharp turn. There's a sudden change in direction. Then when you look at this one right here, it is discontinuous. If I'm graphing this guy, I've got to pick my pencil up and come up here to continue the graph. So we know when we look at this, these are not the graphs of a polynomial function. When we look at the graphs of a polynomial function in general, you're going to see something like this. And they have different shapes, but when you look at this, this is an example. See how you have a smooth rounded turn right here? Same thing here, same thing here. You have a smooth rounded turn here and here. So that's what you're looking for when you're talking about the graphs of a polynomial function. All right, let's talk a little bit about the graphs of polynomial functions and something known as the end behavior. So the end behavior of a polynomial function describes what happens to the function as x approaches both positive and negative infinity. You might hear this in your book as x increases without bound, that just means approaches positive infinity, or decreases without bound, that means x approaches negative infinity. Now the notation for that, this is x increases without bound, or x approaches positive infinity. And then this one right here, this is x decreases without bound, so x approaches negative infinity. The two functions given below, so f of x and g of x, will have the same end behavior. This is due to the influence of the leading term. So this guy right here is exactly the same as this guy right here. So which is commonly referred to as the dominating term when x is large in terms of absolute value. So that means approaching positive infinity or approaching negative infinity. The other terms are going to be insignificant in size. So to prove that to you, I have a little simple example. So we have f of x equals x cubed minus 4x squared plus 2x plus 3, and then g of x equals x cubed. So there's two ways that books usually show this. Some of them use the factor it out approach, which I'm doing here, and some of them will use a table. So you can do that as well. So basically with the factor it out approach, you're going to take this guy right here, whatever it is, and you're going to factor it out. So we're going to show this as f of x equals x cubed times the quantity 1 minus 4 over x plus 2 over x squared plus 3 over x cubed. And then you're just going to think, well, what would happen as x gets really, really large? So as x approaches positive infinity, what's going to happen to this right here, this 4 over x? It's going to get really, really close to 0. 2 over x squared, really, really close to 0. 3 over x cubed, really, really close to 0. And that would be true as x approaches negative infinity as well. So what you're going to have is 1 minus something very close to 0 plus something very close to 0 plus something very close to 0. So basically this guy is going to approach 1 on the inside of the parentheses. It won't be exactly 1, but it's going to get really, really close to 1. And so that would be multiplied by x cubed. So it's going to be really, really close to x cubed. So this guy and this guy will be really, really close in value as x approaches positive infinity or as x approaches negative infinity. Again, the other way you can do this is you can use a table and you can just start plugging in things that are larger and larger. And you can see that for yourself. I'll let you do that method on your own. I've always preferred this factor it out approach. Now let me show you the graph here, and you can make the window different if you want just by playing around with it on Desmos. So this guy in red, that's our g of x equals x cubed. We know what that looks like already. And then in green, that's the f of x equals x cubed minus 4x squared plus 2x plus 3. What's happening to the y values or the function values as x approaches negative infinity? So as it decreases without bound. So I would say that y is going to approach negative infinity. Let me fix this. As x approaches negative infinity. And then let me fix this infinity sign here. I'll make that a little bit better. And then up here, if we think about what's happening to the function values or the y values, well, y is now going to approach positive infinity as x also approaches positive infinity. So for this type of graph, a lot of times your book will say it falls to the left and rises to the right. So falls to the left and rises to the right. You could also use this notation as well. So since the domain of a polynomial function is the set of real numbers, we can use this end behavior to describe parts of the graph we can't sketch. For an odd degree polynomial function, the graph will have the opposite behavior at each end. We just saw that a moment ago. We had it falling to the left and rising to the right. Whereas an even degree polynomial function will have a graph with the same behavior at each end. So if this is our polynomial function, well, what's going to happen is you can use this as a little memory guide. If your leading coefficient here, your a sub n, is positive and your n value is odd, your graph is going to fall to the left and rise to the right. If the case is where a sub n, this leading coefficient, is negative, well, now it's going to rise to the left and fall to the right. Now, when n is even, what's going to happen is if, again, the leading coefficient here, a sub n, is positive, it's going to rise to the left and rise to the right. And then when your a sub n, or your leading coefficient, is negative, again, when n is even, it's going to fall to the left and fall to the right. So notice that in this column right here, so again, this is when n is odd, you have opposite behavior. So this is falling to the left and rising to the right. This is rising to the left and falling to the right. Then when n is even, again, you have the same behavior. So rising to the left and rising to the right, and then down here, falling to the left and falling to the right. So as we discussed above, the end behavior of a polynomial function is determined by the degree n and the sign of the leading coefficient a sub n. Some books refer to the process of finding the end behavior as the leading coefficient test. You will definitely see that, since we're only analyzing the leading coefficient and nothing else. You don't have to worry about anything else in that process. So this is a good image just to get a recap of what's going on. So let's say that your n is odd and your a sub n, your leading coefficient, is positive. Again, we saw an example of this one earlier. Well, y is going to approach negative infinity as x approaches negative infinity, and y is going to approach positive infinity as x approaches positive infinity. Again, we don't know what happens in the middle here. We just know the end behavior. For this one, again, you could say it falls to the left and rises to the right. Now on this one over here, you have a sub n, again, the leading coefficient, is less than 0. So in this case, it rises to the left and falls to the right. So y approaches positive infinity as x approaches negative infinity. And then down here, you have y approaches negative infinity as x approaches positive infinity. So if you're having trouble remembering this, just remember f of x equals x cubed, or you can even do f of x equals x if you want to, and think about the end behavior of this guy. So if you get something where the degree is odd and the leading coefficient is positive, just remember it falls to the left and rises to the right, just like your f of x equals x cubed. Then this one you could use if the degree is odd and the leading coefficient is negative. Here the leading coefficient would be -1. So it's going to rise to the left and fall to the right. All right, so let's look at an example. Here we're given f of x equals x to the 5th power minus 3x cubed minus x minus 1. So if we think about the end behavior of this guy, if we were to graph it, we're going to look at the leading term, which is x to the 5th power, or you could write that as 1x to the 5th power. So the leading coefficient is going to be 1, which is positive, and the degree is 5. So that's going to be odd. So that tells me the graph falls to the left and rises to the right. So if you want to look at the graph, here's the f of x equals x to the 5th power minus 3x cubed minus x minus 1. Again, it falls to the left and rises to the right. So another example, here we're given f of x equals -2x cubed minus 5x squared minus x plus 1. So the leading term now is -2x cubed. The leading coefficient would be -2, which is obviously negative, and the degree is 3, which is odd. So here, the graph rises to the left and falls to the right. So again, looking at this guy, the f of x equals -2x cubed minus 5x squared minus x plus 1, we can see it rises to the left and falls to the right. So the other scenario is going to be where n is even, and in this case, remember, on each n, you're going to have matching behavior. So in other words, with this one, where your a sub n is greater than 0, or you could say the leading coefficient is positive, well, y is going to approach positive infinity as x approaches negative infinity, and then y is going to approach positive infinity as x approaches positive infinity. So for this one, you could say the graph rises to the left and rises to the right. See how it's the same at each end. Then over here, let's say a sub n is less than 0. Again, that's just the leading coefficient if it was negative. Well, now y is going to approach negative infinity as x approaches negative infinity. And then we can say y approaches negative infinity as x approaches positive infinity. So for this, you could say the graph falls to the left and falls to the right. If you're having trouble remembering this, just think about f of x equals x squared. So this is going to be for the case where the leading coefficient is positive, and again, the degree is even. So something like this. So for this one, it rises to the left and rises to the right. Now the other one, let's go with f of x equals negative x squared. Again, you could write that as f of x equals negative 1 x squared, just to make it crystal clear. So you have an even guy right here for the degree, and now the leading coefficient is negative. So this is going to be, again, flipped upside down. We know this is a reflection across the x-axis. And if we look at this, the graph falls to the left and falls to the right. All right, let's look at some examples of this one. So f of x equals 4x to the fourth power minus 2x squared minus 1. Well, the leading term here is this 4x to the fourth power. The leading coefficient is 4, which is positive, and then the degree is also going to be 4, which is even. So for this one, again, you could just think about f of x equals x squared. That guy looks like this. So we know the graph rises to the left and rises to the right. So for this, we have f of x equals 4x to the fourth power minus 2x squared minus 1. Again, clearly you can see it's rising to the left and then rising to the right. All right, another example. So f of x equals negative 2x to the sixth power minus 3x cubed plus x squared plus 2. So the leading term here is negative 2x to the sixth power. The leading coefficient is negative 2, which again is negative, and the degree is 6, which is going to be even. So for this one, again, think about the upside down parabola. So the graph falls to the left and falls to the right. Again, when you're thinking about the end behavior. So looking at this guy, here's your f of x equals negative 2x to the sixth power minus 3x cubed plus x squared plus 2. Again, it falls to the left and falls to the right. Okay, now we want to talk about the shape of the graph near a 0. So this is another piece of the puzzle if you're trying to sketch the graph of a polynomial function. So at this point, we know how to find the zeros of a polynomial function. So we spent a lot of time on that. Recall that a 0 or a root of a polynomial function is a solution to the equation f of x equals 0. So in other words, you can replace f of x or your y with 0 and solve for x. And the real solutions to the above equation are the x-intercepts of the graph. So let me highlight real solutions there. We already know that we might have non-real complex solutions. Those guys are not going to be x-intercepts on your graph. So it's really important to understand that. So when we have a 0 of even multiplicity, so something like 2, 4, 6, something like that, the graph will touch the x-axis and turn around. In other words, it touches but does not cross the x-axis there. Let me stop for a moment and let me come up to the example here. And I'm just going to rewrite this. So this is f of x is equal to, it's x plus 3, but we're going to rewrite that as x minus a negative 3. So it's crystal clear that the 0 there is negative 3. This is quantity squared, and then we have this x minus 2. So we know that here you would have a 0 of negative 3 with multiplicity 2, and then you'd have a 0 of 2. So we know that we would have an x-intercept at this guy right here, which is negative 3, 0, and then you'd also have one right there, which is 2, 0. Now I want you to notice that this exponent here is even. It's 2, so that means, again, this is a 0 of multiplicity 2. Notice that this graph comes up and it touches there and then turns back around. It does not cross through like this one does. Let me go back. When we have a 0 of odd multiplicity, so something like 1, 3, 5, 7, so on and so forth, the graph will cross the x-axis. Additionally, graphs will flatten out near zeros where the multiplicity is greater than 1. So if you have a multiplicity of just 1, it's just going to cross straight through. It's not going to flatten out. So looking at this, here the 0 is 2. Again, you have that x-intercept that's 2, 0. Notice it just crosses straight through. It does not flatten out in any way, shape, or form. Now let me show you this, which is just what we expect when we have repeated zeros. So I'm going to start off with a case where the multiplicity is going to be greater than 1 and your exponent is odd. So a factor x minus k raised to the power of m, where m is greater than 1. So it's not 1, it's not multiplicity of 1. It would be a multiplicity of, let's say, 3, 5, 7, something like that, yields a repeated 0, x equals k, that's just coming from right there, of multiplicity m. Again, that's coming from right there. When m is odd, again, 3, 5, 7, 9, so on and so forth, the graph crosses the x-axis at x equals k. But again, because the multiplicity here, given by this m being greater than 1, we're going to have the graph flatten out. So it's not going to cross straight through like you saw in that example earlier. So it's going to look something like that or something like that. Now, the other case, when m is even, so let's say something like squared, the 4th power, the 6th power, so on and so forth, the graph touches but does not cross the x-axis at x equals k. Again, because the multiplicity here is greater than 1, you're going to see this guy flatten out. Now, the greater the multiplicity, the more it's going to flatten out. Now, let me read this, and then I'm going to go back to that example and explain what's going on. So when you have a 0 of even multiplicity, so let's say it's 2, 4, 6, 8, something like that, the sign of your polynomial function is not going to change from one side of your 0 to the other side of your 0. And that's because when you square something, the result is always non-negative. You're either going to get 0 or something that's positive. If that doesn't make sense for me reading it, it will make sense in a moment when we do the example. So we would say that this means that the graph is going to turn around at the 0 of even multiplicity. Again, because there's no sign change from one side of the 0 to the other side of the 0. If the 0 is of odd multiplicity, so it could be 1, 3, 5, 7, so on and so forth, then the sign of the polynomial function is going to change from one side of the 0 to the other side of the 0, which causes the graph to cross the x-axis at that 0. So it's very important you understand this if you want to make an accurate graph. Let me go back up. All right, so specifically using this example, let's see if we can understand why this is turning around here, but crossing through here. Why is that the behavior of this guy? Well, if you think about setting up some intervals, something like anything that's less than -3, so from -infinity to -3, both are excluded there. We're using the open interval notation. And then between -3 and +2, again, both are excluded there. And then anything larger than 2. Remember that we're multiplying these guys together to get the y value. So you plug something in for x, plug it in there, plug it in there, multiply these two guys together, you get your y value. Well, if you think about this factor x minus 2, this is going to be negative in this interval here and also this interval here. Because something like x minus 2, actually we can just say, where is that greater than 0? That's very simple to solve. You add 2 to both sides of the inequality, this cancels, and you get x is greater than 2. So it's only going to be positive for x values that are greater than 2. It would be negative here and negative here. So what that tells me is that if I look at this other factor here, which is x plus 3 quantity squared, this guy is always going to be non-negative. It can be 0 when x is -3, so that's right there, but it's going to be positive everywhere else because of the squaring. So okay, if this guy is multiplied by this guy, then I already know, again, just using my little sign chart here, that anything to the left of -3 will have a negative times a positive, which gives me a negative. So I'm going to be below the x-axis, again, where the y values are negative. Then when I think about being in this interval right here, well, again, this guy's positive, this guy's negative. So a negative times a positive gives me a negative. So I'm below the x-axis. My y values are negative. So think about what's happening here. I'm negative, 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 negative. I come up to the point where x equals -3. And so you get, again, let me write this out. So this would be -3 plus 3 quantity squared. And then times you would have -3 minus 2. All I'm doing is plugging in for x there. So this right here would be 0 squared, which is 0, times -3 minus 2. That's going to be -5, which is going to be equal to 0. So this goes from negative, negative, negative to 0. And then on the other side of that, what's happening is we're going back to having a positive times a negative again. And so we're going to be negative, 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 negative. And that's going to continue until we get to an x value of 2. When you get an x value of 2, again, this guy is going to be 0. And then when the x value is greater than 2, well, now you have a positive times a positive, which gives you a positive. So this is negative, negative, negative. It turns to 0. And then once we're greater than 2, we're going to be positive. So notice that you had a sign change from this side of 2 to this side of 2. So that's why we're crossing through. But when we looked at this one right here, there was no sign change. We were negative, 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 and then we went to 0. We never go to positive, then we go back to negative, negative, negative. So that's why this guy is going to come up. It's going to touch and turn around, and then this guy's going to come up and now go through. So hopefully that does make sense. We're going to do another example so you can pause the video and think about that one on your own. Let me go down to that one. So here we have f of x equals the quantity x minus 1/2 cubed, then times the quantity x plus 2 squared, then times the quantity x minus 2. So we know that we would have a 0 of 1/2 and the multiplicity would be 3. We have a 0 of, this would be -2, the multiplicity would be 2. And then we have a 0 of +2, the multiplicity would be 1. Let's write that out. So for the zeros, we have 1/2, the multiplicity, and I'll just abbreviate that, is 3. Then we're also going to have -2, and the multiplicity, so the multiplicity there, would be 2. Then lastly, this is x minus 2. You could put a 1 there for clarity. So let me just say that the last 0 here would be 2. A lot of times if the multiplicity is 1, we don't write it. But just for clarity here, I'm just going to write it. So the multiplicity is 1. So let me make a little border here. And let's think about what we would expect. So these are the x-intercepts. So we're going to have 1 at 1/2, comma, 0. Now the multiplicity for that 0 is 3. So I know that this is going to cross through the x-axis there. And I also know because the multiplicity is 3, it's greater than 1. So it's going to flatten out near that 0. Then you also have one of -2, comma, 0. So the multiplicity here is 2. So that's even. And so this guy is going to touch and turn around. And also this will be a little bit flattened out because the multiplicity is 2, which is greater than 1. Then you're also going to have this guy right here, which is going to be 2, comma, 0. Now the multiplicity here is 1. So again, when you think about that, it's just going to cross straight through and it's not going to flatten out because the multiplicity is just 1. So let's go down and confirm what we just said. So this guy right here, that is your -2, comma, 0. Again, coming from this right here, x minus a -2, quantity squared. Notice that it's going to touch and turn around. When we look at this guy right here, this is 0.5 or 1/2. Again, that's coming from right here. We know it's going to go through, but notice that here it flattens itself out a lot. And that's because the multiplicity is 3. If you have something like 3 or 5 or 7 like that, it's going to flatten out when you go through on that 0. Let me label this. You can put 1/2, comma, 0, or again, you could use 0.5 if you want. That's just going to be personal preference. And then this one right here is going to be for 2, comma, 0. Again, the multiplicity there is 1. Notice that it doesn't flatten out there. It crosses through, but it just crosses straight through. It doesn't flatten out in any way. So that's just something you need to understand when you're looking at your zeros and you're planning on how you're going to set those up when you sketch your graph. Okay, so before we actually get into sketching the graph of a polynomial function, we need one more piece of the puzzle. So we're going to talk about turning points. Your book might title this as local maxima and minima. So polynomial functions often have turning points. So where the function changes from increasing to decreasing or from decreasing to increasing. So these turning points will be referred to as a local maximum point, also known as a relative maximum point. You might hear that as well, when the function takes on a greater value than any nearby points. So you're thinking about the y value. Is it larger than any nearby points? That's going to form what we call a hill. And I'll show you that in a moment. And a local minimum point, also known as a relative minimum point, when the function takes on a lesser value than any nearby points. So is the y value smaller than the y value of nearby points? So that's going to look like a valley. Let me just go to this little example here. Local maximum points, you have points A, so that's this right here, and C on the graph. Notice that the y value here is greater than the y values around it. We are not saying that it's the largest y value on the graph. It's just what's in the local viewing window. That's how you're thinking about this. This forms a hill. This forms a hill. Another way to think about it, remember earlier on, we talked about increasing and decreasing those intervals. I drew a little guy that was walking. So let's just say this guy is walking, and right now you are increasing. So right here, you're going to change that over, and now you're going to be decreasing. So where we change here is at this point A. So that forms what we call a local maximum point. We're changing from increasing to decreasing. Now this guy's going down. And you could do the same thing if you wanted to draw it. You're increasing here, and then at C, you're going to change over, and now you're going to start decreasing. All right, the other one, we talk about local minimum points. So points B and D on the graph. Notice how that looks like a valley here and a valley here. Again, we're not saying that the y value here is the smallest on the whole graph. It's just in a local viewing window. You can see that the y value here is less than those around it. Same with the y value here. It's less than those around it. If we think about, again, doing this with our walking guy, you're changing. So right here, he is decreasing, decreasing, decreasing. When we get to that point B, we're changing over to increasing. So now this guy is going to be walking up. So just think about it that way. If you're changing from decreasing to increasing, that's going to form a local minimum point. If you're changing from increasing to decreasing, that's going to form a local maximum point. All right, so when you hear the terms maxima and minima, these are just the plural forms of the words maximum and minimum, respectively, coming from Latin. The local maximum and minimum points on the graph of a polynomial function are called its local extrema. So this is something that you'll definitely see in this section. A lot of times for your test or for your homework, you're going to be given a graph and you're going to be told to find the local extrema. I have a note here. So without the use of some basic calculus, so this would involve derivatives, it is usually not possible, or at least extremely impractical, to find the actual turning points for a polynomial function when the degree is greater than 2. So what I'm talking about there is that you don't have a graph. So you're not using Desmos, or you're not presented with a graph or something like that. And they just give you the function and they say, hey, go ahead and find the local extrema. That's something we're going to be able to do once we get to calculus and we learn about derivatives. All right, before we move on, I want to stop here and just cover a very common source of confusion. So when you deal with local extrema, and you'll deal a lot with this in calculus, you want to understand the question that you're being asked, because it can be asked in different ways, and so you would give different answers. What we've done so far is we've been working with points. So I would say something like, what are the local minimum points? So those are x comma y. Or what are the local maximum points? So those are x comma y. So those are turning points. And this is in the context of graphing a polynomial function. We need points. So you have to understand the difference between how things are being worded. So I have here, what's the difference between where a function has a local, or again, you could say relative, maximum or minimum, and the local, or again, you could say relative, maximum or minimum. So if f of x sub 1, remember that's a y value, that's us plugging in x sub 1 for the function and evaluating. So f of x sub 1, that's a y value or a function value. So if f of x sub 1 is greater than all other values of f, and we're talking about y values there, near x sub 1, then f has a local, or again, you can say relative, maximum at the input value x sub 1. So again, if they're asking you where, you're going to see the keyword at used when you answer. So it's at, and you can give your x value. Now, sometimes the teacher will say specifically that they want the point. So then you give the x comma y. Then we have the local, or again, you could say relative maximum. So we're talking about that there is the output value. So the f of x sub 1, so that y value there. So we could say that f of x sub 1 is a local, or again, you could say relative, maximum value of the function. So just keep that in mind. And it's the same thing for this one when we talk about a minimum. So if f of x sub 2 is less than all other values of f near x sub 2, then f has a local, or again, you could say relative, minimum at the input value x sub 2. So again, if they're asking you where, you're typically saying it's at, and you give the x value. Then you could say the local, or again, relative, minimum is the output value. So that's your f of x sub 2. So we could say that f of x sub 2 is a local, or again, relative, minimum value of the function. So just keep that in mind if you get questions about local extrema. Okay, one more thing before we look at an example. So a polynomial function of degree n has at most n minus 1 turning points. So let's say the degree was 3. The most number of turning points you would have would be 3 minus 1, which is 2, with at least one turning point between each pair of consecutive real zeros. So keep that in mind. I have a note here. Be careful here, as we are only saying that a polynomial of degree n has at most n minus 1 turning points, not that it will have n minus 1 turning points. So a polynomial function of degree n may have less than n minus 1 turning points. So you may get something that's a 5th degree polynomial that does not have 4 turning points. We are only saying here that it has at most 5 minus 1, which would be 4 turning points. Okay, let's look at an example real quick. So I have this graph already drawn. So let me write this out. It's a little bit hard to see. So f of x is equal to, you're going to have 1/4 times the quantity, x minus 1, and then times the quantity, x minus 3 squared, and then times the quantity, x plus 2. Again, I've given you this on Desmos. Your degree here, if you want to go through and simplify, it's going to be 4. And so you can see you have 1, 2, 3 turning points, but it doesn't always work out that way. But we know that, again, if the degree is 4, it's going to have n minus 1, so that would be 3, turning points at most. But it doesn't mean it has 3, just at most. If I asked you, what are the local minimum points and what are the local maximum points? Again, I'm asking for points, so I want x comma y. So I'm going to write out local minimum points. And then let me write out local maximum points. Again, your teacher may ask for this in a different way. I am specifically asking for x comma y. They may want the y values just depending on how they phrase this. That's why I spent so much time on that little reading earlier. But if I look for the local minimum points, so I'm looking for where it's going to go from decreasing to increasing. So this is decreasing and then changing to increasing. So this is going to be -1 comma -8. So that's going to be a local minimum point. So -1 comma -8. So we're going to come back up here. Forget about this for right now. We're going to come back down. So this right here, again, we're changing from decreasing to increasing. So this forms a little valley here. So another local minimum point, you're going to have that at 3 comma 0. So you have two of those here. One right there, again, you're changing from decreasing to increasing, and then one right there, again, changing from decreasing to increasing. Now, in terms of your local maximum points, you just have one here. So it's going to occur right there. You're changing from increasing to decreasing. Again, this is forming a little hill. So that one's going to be 1.75. And this is an approximation. So let's just say it's about 1.099. All right, now let's wrap things up. I'm going to give you a little procedure for creating a rough sketch of the graph of a polynomial function. So I want you to keep some things in mind here. You are not a computer. You are not going to make a perfect graph, and you don't need to. As we move forward in math and we get into stuff like calculus, where we can take derivatives and things like that, we will be able to make a more accurate graph because we'll understand where the turning points are. Even when we get into calculus, it's still not going to be perfect. You can always use a graphing calculator like a TI series or Desmos, some online graphing calculator, if you need a perfect graph. This is just about learning the concept. So here I'm going to start off by saying that we can use the leading coefficient test to find the graph's end behavior. So what's happening as we go to the very far left and what's happening as we go to the very far right. So just the end behavior. Then we're going to find the x-intercepts by solving the equation f of x equals 0. So again, we're looking for the real solutions to that equation. So those guys are going to be the x-intercepts. If you have a non-real complex solution, remember that's not going to be an x-intercept. If k is a zero of even multiplicity, keep in mind the graph touches the x-axis at x equals k and then turns around. If k is a zero of odd multiplicity, the graph crosses the x-axis at x equals k. And we know if the multiplicity of k is greater than 1, the graph flattens out near k comma 0, so at that x-intercept. Then we want to find and plot the y-intercept. So find the y-intercept as 0 comma f of 0. This right here is not always practical. Sometimes if you're working on something, you might get a y-intercept that's something like, let's say 0 comma 500. You can change the scale of your graph, but it's not always practical. So I would say this one right here, you want to know what it is just to see if you're on the right track, but sometimes you won't be able to fit it in unless you really change the scale. All right, we have use symmetry when available to sketch the graph. So you can't always use this. So y-axis symmetry, f of negative x equals f of x. Origin symmetry, f of negative x is equal to the negative of f of x. So sometimes you can use that to help. And then we have use test points within the intervals formed by the x-intercepts to find the sign of f of x in the interval. So since the graph of a polynomial function is continuous, remember no holes or breaks, the values of f of x are either always positive or always negative in a given interval. What do I mean by that? Well, the interval you're creating is going to be between the x-intercepts. So we're not going to have a y value of 0 unless we're on an x-intercept. So if you're between those x-intercepts, you're either above the x-axis or you're below the x-axis, again, because the function is continuous. So when the values are positive, we are above the x-axis, right? The y values are positive there. When the values are negative, we are below the x-axis. Again, the y values are negative there. Then you can use the maximum number of turning points of n-1 to check the graph. Remember, it doesn't have to have n-1 turning points, but that's the maximum number that it can have. So if you have a function with a degree of 5 and you have 7 turning points, you did something wrong. Okay, let's look at the example. So here I have f of x equals the quantity x minus 3 squared, and then times the quantity 2x minus 1. And I've put this right here as f of x equals 2x cubed minus 13x squared plus 24x minus 9, if you want to see it being simplified. So what is the first step? We're going to think about the end behavior. So the leading coefficient is 2, which is positive, and the degree is 3, which is odd. So that tells me, again, just think about f of x equals x cubed. It falls to the left and rises to the right. So if you look at the little graph, and I'm going to fill the rest of it out in a moment, you see here I have that it falls left and rises right. And you don't have to worry about it. I know it's going to come something like that. Just put this to the far left and to the far right like this, and just show your teacher you know what's going to happen. We need to get the x-intercepts. And again, for that, you're just going to say x minus 3, quantity squared times 2x minus 1 is equal to 0. Well, one of your zeros is going to be 3 with a multiplicity of 2. So let me write the zeros here. You're going to have 3. And then the multiplicity is 2. And then the other one, you set 2x minus 1 equal to 0. So 2x minus 1 equals 0. Add 1 to both sides of the equation. This cancels. You get 2x is equal to 1. Divide both sides by 2. This cancels. You get x is equal to 1/2. Now, if you want to do this, and some teachers will tell you to, you can actually factor this. Let me put like this. You can pull a 2 out. So if I pull a 2 out from here and put it out here, well, what happens is I divided this by 2 and I just get x. 2x over 2 would be x. And then I have to divide -1 by 2. So this is -1/2. So that's another way to do it if you want, to just write everything in the form of x minus k. And so you have 1 0 of 3, which again has a multiplicity of 2. And then you have another 0 of 1/2, which I'm just going to write. Normally we don't, but we'll just say the multiplicity is 1. So we know the x-intercepts here would be, this one is 3, 0. And again, it's going to touch there and turn around. And this one would be 1/2, 0. And there it's going to cross straight through. So here is your 3, 0. Again, it's going to touch and turn around. And then here is your 0.5, or you could say 1/2, 0. And it's just going to go straight through. We need our y-intercept. So how do we get that? Again, you plug in a 0 for x. So f of 0 would be equal to, again, all this would just go away because 0 cubed is 0, 0 times 2 is 0. 0 squared is 0, 0 times -13 is 0. 0 times 24 is 0, so you just have 0 minus 0 plus 0, that's just 0. So you're really just left with that -9 there. So you would get 0, -9, which in this case would fit on a graph. It would not be a problem. So 0, -9, that's going to be down there. All right, so at this point, I'm going to set up a little table and just get some additional points. So you'll see here that I have interval, I have the x value that I'm going to pick, and then the f of x or the y value that I'm going to get. So where am I getting these intervals from? Again, like I talked about in the procedure, it's just coming from the x-intercepts. So at the x-intercept, we know that the y value is 0. So that's going to be at an x value of 1/2, and then also at an x value of 3. But if you're not at an x-intercept, well then we know that the y value is either going to be positive or it's going to be negative, meaning I'm going to be above the x-axis or below. So you're going to pick something in the interval where x is less than 1/2, and you're going to see if I plug that in, do I get something that's positive, meaning I'm above the x-axis, or negative, meaning I'm below the x-axis? Then you're going to do the same thing. You're going to pick an x value between 1 and 3, and then you're going to do the same thing, and you're going to pick an x value that's greater than 3. So let's come back down, and I have here some values are rounded. So in this interval where x is less than 1/2, I'm just going to pick an x value of 0.295, and the y value here is about -3. Not exactly, but pretty close. Then in the interval between 1/2 and 3, the x value I'm going to pick is 1. The y value I'm going to get out is 4. Then in the interval where we're greater than 3, we're going to pick an x value of 3.78. And this right here, we're going to get a y value of about 4. Again, this is rounded here, so it's not exactly 4, but it's pretty close. So I've added this 0.295, -3, this 1, 4, and this 3.78, 4. So that gives me more points. Again, that allows me to sketch something that's more accurate. So what we can do here is a little estimation technique. And I would start with something like f of 1, which equals 4. Again, that just comes from the point 1, 4 that we just found. Again, I'm trying to find a local maximum. Let me go back real quick, just so this is crystal clear. Again, at this point, we know the graph is going to come up like this. So we know we're going to be increasing, and at some point we're going to switch over. That would be the turning point, and we're going to start decreasing. And then here we're going to have a local minimum. So this is a turning point, and then we're going to come back up. We're going to start increasing again. So what we need to figure out is where this guy is going to go from increasing to decreasing. So where does it change over? That's the turning point. That's the local maximum. So if you start with this f of 1 equals 4, now what I'm going to do is look at f of, and again, I'm just going to pick 1.25. You could do f of 1.1 or f of 1.05. It's just a matter of what you want to do. So f of 1.25, this is equal to 4.59375. So this y value is larger than this y value. So then I'm going to do that again. We have f of 1.3. This equals 4.624. So this y value is larger than this y value. Then I'm going to do that again. So we have f of 1.35. So that's equal to 4.62825. So this y value is greater than this y value. And then I'm going to do that again. So f of 1.4 is equal to 4.608. So now this y value is smaller than this y value. And if you look at f of 1.5, this equals 4.5. So this y value is smaller than this y value. So what does that tell me? That tells me that this guy right here, which gives me the largest y value, so in other words, 1.35, 4.62825, out of what I looked at, that's a good place to turn. It's not going to be exact, but it's a good place to turn because you're looking for where this guy's going to go from increasing to decreasing. Look at your y values. You have 4, then you go to 4.59375, then you go to 4.624, then you go to 4.62825, and then you start dropping off. So you go to 4.608, 4.5. So I don't know exactly where this happens, but I can just say that this 1.35, 4.62825, that's a good place to turn. Now, in the future, when we get to calculus, we'll be able to find the exact turning points, but we need derivatives for this. So something like the derivative of our polynomial function, that's f prime of x is equal to 6x squared minus 26x plus 24. You would take that and set it equal to 0 and solve. So we know how to do that already. So you get x equals 3 and then 4/3. Now, if we come back, again, we already know the 3 one. That's a local minimum. But the one we didn't know was the 4/3, which is 1.3, where the 3 repeats forever. So coming here, we said it's about 1.35, so that's pretty close. Now, for the purposes of graphing, we need the y values, so you would just plug in and get that. So we know 3, 0 already. The other one, this would be 4/3, 125 over 27. So even without calculus, we were able to get pretty close. And at this point, all we have left to do is just to sketch our graph. Again, this turning point, just get it as close as you can. You have the other points there. So you would just sketch this guy like this. I have a computer drawn one, so of course that's going to be drawn perfectly. Your graph does not need to be perfect. Just get it as close as you can. In this lesson, we're going to talk about graphing rational functions. All right, let's start off with the definition of a rational expression. So a rational expression is the quotient of two polynomials with a non-zero denominator. Remember that we cannot divide by 0, so that's undefined in math. So a rational function is a function that is defined by a rational expression. So here we've set up a little function. We have f of x equals p of x over q of x, where again, q of x is not equal to 0. So p of x and q of x, those are polynomials, where again, q of x, this guy in the denominator, is not 0. So the domain of a rational function consists of all real numbers, except those for which the denominator equals 0. So let me give you one example here. This is f of x equals x minus 3 over 2x squared minus 13x plus 15. If I ask you for the domain for this guy, how would you get it? Well, again, it's all real numbers except those that make the denominator 0, because you can't divide by 0, that's undefined. So what you want to do is you want to take this right here, this denominator, which is 2x squared, and then minus 13x, and then plus 15, and you want to set it equal to 0, and you want to solve that equation. So the solutions that you get for this, again, make the denominator 0, so you have to exclude those values from the domain. And we can solve this with factoring. This is a pretty easy one overall. This is 2x squared, so I'm going to put a 2x here and an x here. Notice that this is a minus and this is a plus, so that means I want a minus here and a minus here. And then for this 15 right here, just think about the positive factors. You have 1 and 15 or 5 and 3. So 1 and 15 is not going to work. You're going to need to use 5 and 3. So what you want is a 5 here and a 3 here. And then when you check this, your outer, 2x times negative 5, that's negative 10x. And then your inner, negative 3 times x, that's negative 3x. When you add your outer and your inner, so negative 10x plus negative 3x, that's going to be negative 13x. Okay, so what we're going to do is use our zero product property. So 2x minus 3, this factor right here, we're going to set that equal to 0. Then or, we're going to take this factor, which is x minus 5, we're going to set that equal to 0. So we're going to add 3 to both sides of the equation, and this right here is going to cancel. We're going to get 2x is equal to 3, and then we're going to divide both sides of the equation by 2, and so let's cancel this with this, and we get x equals 3 halves. Over here, let's add 5 to both sides of the equation, so this cancels. We're going to get that x is equal to 5. So you get x equals 3 halves, or x equals 5. Let me actually write that like this. I'm just going to put x is equal to 3 halves. I'll just put a comma, and then you could say x could also be 5. So these two values right here would make the denominator of that rational function 0, so they have to be excluded from the domain. So when we come back up and write our domain here, we're just going to say it's the set of all x such that x is not equal to, you would have 3 halves, and then also 5. All right, let's take a look at graphing y equals 1 over x. So the most basic rational function with a variable in the denominator is this y equals 1 over x, or f of x equals 1 over x, if using function notation. This function is known as the reciprocal function, which we studied earlier in the course. We did a lesson on parent functions, and we also did quite a few lessons where we looked at graphing transformations. So we should know the graph of f of x equals 1 over x at this point. So the reciprocal function pairs every non-zero real number with its reciprocal. Since x is in the denominator, x can't be 0. All right, so what we're going to do now is just review the graph of f of x equals 1 over x. We're also going to talk about the features of f of x equals 1 over x. So we'll just kind of do those together. The idea here is that we've already seen this graph a lot. Again, when we're doing graphing transformations, we use this a lot as the parent function. And when you're in this section, the first problems that you get, you can graph them using graphing transformations. And if you know these 6 points that I'm going to go through here, it's very easy for you to complete those problems. So essentially, the first point I have here is -2 comma -0.5, or you could say -2 comma -1/2. Then you have -1 comma -1. And then -0.5 comma -2, or of course you could say -1/2 comma -2. And then up here you have 0.5 comma 2, or again you could say 1/2 comma 2. You have 1 comma 1, and then you have 2 comma 0.5, or again 2 comma 1/2. So this point, this point, this point, this point, this point, this point, that's really all you need, along with the fact that you have a vertical asymptote, which is x equals 0, and a horizontal asymptote, which is y equals 0. So if you know that, you can make this graph pretty easily. Then when you think about the features of your f of x equals 1 over x, again, just think about the graph that we just looked at. The domain is the set of all x such that x is not equal to 0. Again, what did we talk about earlier when we talked about the domain? Well, it's all real numbers except for those that make the denominator 0. How can I make the denominator 0 here? Well, I would just plug in a 0. So I would have to exclude 0 from the domain, but anything else is okay. Now, in terms of the range, that one's pretty easy to think about as well. Let's replace f of x with y, and then you could replace y with a 0, and you can think about why this is not possible. So this equation that I've just set up is going to be one that has no solution. When you think about this right here, this 1 over x, this is a fraction, and for a fraction to have a value of 0, the numerator needs to be 0, and the denominator needs to not be 0. Well, how can I get a numerator of 0 here when the numerator is 1? That's a constant, it's never going to change. So this right here, this 1 over x equals 0, that's impossible. There's no value for x such that 1 over x would be equal to 0. So this has no solution. So that means the range would be the set of all y such that y is not equal to 0. Okay, when we think about this part right here, so f of x equals 1 over x decreases on the intervals. Let me go back up. So just thinking about it, it's this piece right here. So this is where x is less than 0. So in interval notation, this piece right here, this is you're coming from negative infinity, going up to and excluding 0. And then also this piece right here. So this is anything greater than 0. We're also decreasing on that interval. So this would be anything larger than 0. Again, this is just going out to positive infinity. Then you have that the graph is discontinuous at x equals 0. Again, because we can't divide by 0, that's undefined. The line x equals 0 or the y-axis is a vertical asymptote. Then we have the line y equals 0 or the x-axis is a horizontal asymptote. And then the reciprocal function f of x equals 1 over x is an odd function. So again, we've talked about this a lot. The graph is symmetric with respect to the origin. Okay, so in this section, we're going to use something called arrow notation. If you take a Calculus 1 course, you're going to see this a lot. So this might be new for you, but it's really not that bad. It's just something you need to practice with. So first we have this f of x. This means approaches, or you could say goes to, when you see this arrow here. So this is negative infinity as x approaches 0. And then this right here, this little negative sign, that means from the left. So if you read this, it's y approaches negative infinity as x approaches 0 from the left. So that's what this is meaning right here. Then if you look at this one, you have f of x, or again y, approaches, this would be positive infinity as x approaches 0. This plus sign here, that means from the right. So this is from the right. So the reason we have to be specific there, if we come back up to the graph, and I'll also show you this with a table, think about this piece of the graph right here. So what we're saying is that y approaches negative infinity as x approaches 0, but we have to be very specific here. We can't just say approaches 0 here, because what if I'm approaching 0 on this side right here? Well, then the y values would approach positive infinity. So to be specific, we're going to include this notation here. We're going to put this little minus there up at the top. So that means from the left. So coming from the left, I'm talking about this guy right here. So coming this way from the left, as my x values get closer and closer to 0, my y values are, again, decreasing without bound. I'm approaching negative infinity. For this piece of the graph right here, as the x values get closer and closer to 0, well, now the y values are increasing without bound. So I'm approaching positive infinity. So again, I got to be specific. So for this one, we would say y approaches positive infinity as x approaches 0. Again, this is going to be from the right. So I want to make sure I put that plus sign right there to say from the right. So that's why we have this different notation here in case that's a little bit confusing. So another way to do this, and you'll see this in your textbook, is with using a table. So just another way to think about it. So you have f of x or y approaches negative infinity as x approaches 0 from the left. So using a table, you could just think about, well, here's 0 on the number line. If I'm to the left of 0, where the values are negative, again, I'm getting closer and closer to 0 coming from this side without touching it. So you have -1 here, but then you can get closer by saying -1/2, then you could do -0.1, then you could do -0.01, and so on and so forth. So what's happening is you're decreasing without bound, and your y values are approaching negative infinity as you get closer and closer to 0. You can get as close as you want, you just can never touch it. Then similarly, if we think about this one, so f of x or y approaches positive infinity as x approaches 0 from the right. So that's me coming over this way. Again, I have 1 here, but again, I can get closer by saying 1/2, then I could do 0.1, 0.01, so on and so forth. What's happening is as I get closer and closer to 0, the y values are now increasing without bound, so I'm approaching positive infinity. So putting these two things together, you could say in terms of absolute value. So remember absolute value that takes something that's negative, it makes it positive. So the absolute value of f of x or the absolute value of y approaches positive infinity as x approaches 0. So this is either from the left or the right. And the reason we're able to say this is because of these absolute value bars here. So keep that in mind. So as x gets closer to 0, coming from either the left or the right, the y values in terms of absolute value, so that's the key here, get larger and larger. Since x can't actually be equal to 0, our graph will never intersect the vertical line x equals 0. As we have previously seen, this line is known as a vertical asymptote. So that's where that's coming from. All right, so for the next two, we have f of x or y approaches 0 as x approaches negative infinity. That's pretty straightforward. And then similarly, we have f of x or again y approaches 0 as x approaches positive infinity. Again, just coming back to the graph, you can think about it this way, or you can also use the table. I'll just do both with you. So think about this piece right here. What's happening to the y values or the function values as x increases without bound? So in other words, what's happening as x goes to positive infinity? Well, the y values are getting closer and closer to 0. So we can say that y approaches 0 as x approaches positive infinity. Well, then if I look at this piece over here, where x is decreasing without bound, so as x approaches negative infinity, you could say that y is also approaching 0. So we're going to say y approaches 0 as x approaches negative infinity. So again, you can also think about this with a table. You'll see this in your book. So you have f of x or y approaches 0 as x approaches negative infinity. So just thinking about that, x now we're thinking about as it decreases without bound. So as we keep going this way on the number line, so you can see I have a little table here. So if you plug in something like -10 for x, 1 divided by -10 would be -0.1. And again, you can just make this more and more negative. So something like -100, you plug that in, 1 divided by -100, you get -0.01. And you're going to keep getting closer and closer to 0 without actually touching it as this guy gets to be a larger and larger negative number. Now, the other one, let me erase this, we have f of x or y approaches 0 as x approaches positive infinity. So this way is where we're going now. So as we increase without bound, so we approach positive infinity. Again, it's a similar concept here. So 1 divided by 10, you get 0.1. Then 1 divided by 100, you get 0.01, and so on and so forth. You can just keep making this number bigger and bigger, and you're going to keep getting closer and closer to 0. So to summarize this, we can say f of x or y approaches 0 as, and again, this is why we can write this because of the absolute value bars, the absolute value of x goes to positive infinity, or you could say approaches positive infinity. So as x gets large in terms of absolute value, so as the absolute value of x goes to positive infinity, the y values get close to 0. So in other words, the graph will get closer and closer to the horizontal line, y equals 0, which is known as a horizontal asymptote. All right, let me give you a quick summary of the arrow notation, just in case it's not clear for you, because this is definitely going to come up in this section. And then again, if you get into calculus, you're going to see it a lot. So this right here means x goes to, or you could say approaches a from the left. When we say goes to or approaches, we're saying that it gets very, very close as you would like without actually getting there. In other words, we looked at x approaches 0 from the left. So coming from the left, we're approaching an x value of 0, but we're never going to actually get there. So that's what that means. Then this one is x approaches, or again, you could say goes to a, and this is from the right. So you would just change this like this, and you would say x approaches 0 from the right. Then the other two, we have x approaches or x goes to negative infinity. So we can say also that this is x decreases without bound. Then this one is x goes to or x approaches positive infinity. So in this case, you might hear x increases without bound. All right, so at the beginning of this section, you're going to be able to use graphing transformations to graph your problems. So this is going to be graphing transformations of y equals 1 over x. So you could say f of x equals 1 over x. So I have here a simple rational function of the form g of x equals ax plus b over cx plus d. So if you get something that looks like this, so something like g of x equals 2x plus 8 over x plus 2, you can use graphing transformations for this. Now, it might not be obvious how you're going to do that, but essentially, if you compare this to f of x equals 1 over x, before doing anything, you might be stuck. So what do I do? Essentially, you're just going to do long division, or in this case, you could do synthetic division to set the problem up. Let me put a little border here. You would say that this is 2x plus 8 divided by, remember, you want this in the form of x minus k. So we're going to go x minus a negative 2. Let me switch over the color here for that, so this is clear. And so essentially, you're going to set up your little synthetic division. So put your negative 2 out here, and then your 2 here and your 8 here. Drop down the 2. Negative 2 times 2 is negative 4. 8 plus negative 4 is positive 4. So this right here, again, it's 1 degree less. Well, we were working with a first degree, so 2 would just be the constant. And then this would be the remainder. So coming back up, let me get rid of this. And you can get rid of this for a moment. Let's just say this would be equal to, well, again, the quotient was 2, and then plus the remainder was 4. And you want to write that over your divisor here, or your denominator. So this would be x plus 2. Well, if I look at it like this, now that looks like something I can use graphing transformations for. If I put f of x equals 1 over x, and then g of x equals 4 over x plus 2, and then plus 2, what you'll notice is that you could write this as g of x is equal to 4 times f of, you would have x plus 2 there, and then plus 2. This 4 right here is giving me a vertical stretch by a factor of 4. This plus 2 on the inside, again, for horizontal transformations, you have to undo what's being done to x. So it's x plus 2. So to undo that, I need to subtract away 2. So this part right here means I need to shift left by 2 units. Not right, left by 2 units, because you have to undo things on the inside. Then this plus 2 right here, that's going to mean me shifting up by 2 units. So if you have an x comma y on your original f of x equals 1 over x, when you go to g of x, it's going to be x minus 2, again, because we're going to shift left by 2 units, comma, 4y, again, you have a vertical stretch by a factor of 4, so you're multiplying y by 4, and then plus 2 because of the shift up by 2 units. So I'm just going to show you some points. These are, again, from earlier on, and you can go through and pause the video and just verify these, but essentially something like negative 4 comma negative 0.25, that's going to go to negative 6 comma 1. Negative 2 comma negative 0.5, that's going to go to negative 4 comma 0. Negative 1 comma negative 1, that's going to go to negative 3 comma negative 2. Then negative 0.5 comma negative 2, that's going to go to negative 2.5 comma negative 6. Then 0.5 comma 2, that's going to be negative 1.5 comma 10. 1 comma 1 is going to go to negative 1 comma 6. 2 comma 0.5 is going to go to 0 comma 4. And then 4 comma 0.25 is going to go to 2 comma 3. So looking at the graph, this is going to be for g of x equals 4 over x plus 2, and then plus 2. Again, just using graphing transformations to get these points. So you have negative 1.5 comma 10, negative 1 comma 6, 0 comma 4, 2 comma 3. So that's going to be for this branch right here. And then you have negative 6 comma 1, negative 4 comma 0, negative 3 comma negative 2, and then negative 2.5 comma negative 6. That's going to be for this branch right here. Now, in terms of the asymptotes, how do I know I have x equals negative 2 as the vertical asymptote, and then y equals 2 as the horizontal asymptote? Well, when you think about this, moving your vertical asymptote, that's going to deal with any horizontal shift that you have. In this case, the horizontal shift, again, because you have that plus 2 there, you need to undo that, so it's minus 2. You're going 2 units to the left. So normally, the vertical asymptote is x equals 0, or the y-axis. But again, because we shifted it 2 units to the left, now it's going to be x equals negative 2. Then in terms of the horizontal asymptote, again, normally that's the x-axis, or y equals 0. You're just going to look at your vertical shift, so that's plus 2. You're going up 2 units. So now that becomes y equals 2. So that's how you would get that. All right, now let's talk about another one that's common in this section. So graphing y equals 1 over x squared, or again, f of x equals 1 over x squared, and transformations. So another very common rational function is y equals 1 over x squared, or again, f of x equals 1 over x squared if using function notation. So f of x equals 1 over x squared is even, meaning it has y-axis symmetry. So similar to the reciprocal function, the graph has a break. It is made up of 2 distinct branches. So coming down to the graph, again, this is one that we've seen before. So for f of x equals 1 over x squared, if you have an x value of either positive 2 or negative 2, you're going to get a y value of 1/4. Again, we know that squaring a number, if it's negative and you square it, you get a positive. If you square a positive, you keep a positive. So 1 over negative 2 squared, that's 1/4. Then 1 over 2 squared, that's also 1/4. So you get this point right here, which is negative 2 comma 0.25, and this point right here, which is 2 comma 0.25. Then similarly, if you have positive or negative 1 for the x value, you're going to get positive 1 for the y value. So negative 1 comma 1 and 1 comma 1. If you have positive or negative 1/2 for the x value, you're going to get 4 for the y value. So you have negative 0.5 comma 4 and then 0.5 comma 4. Then again, at an x value of 0, you're going to have undefined, because if you had 1 over 0 squared, that's 1 over 0, that's undefined. So you'd still have a vertical asymptote at x equals 0, and you'd also have a horizontal asymptote at y equals 0. All right, let's talk about the features of y equals 1 over x squared. So first and foremost, we have our domain, where we say the set of all x such that x is not equal to 0. Again, because we have this x squared in the denominator. When we look at the range, we would say the set of all y such that y is greater than 0. So again, y can't be 0. So if you look at y equals 1 over x, or you look at y equals 1 over x squared, in each case, y can't be 0. Now, in this case on the left, the first parent function that we looked at, your y values could be negative. And that's because you can plug in something negative for x there. And so let's say you had negative 1. 1 over negative 1 would be negative 1. So a point on this graph would be negative 1 comma negative 1. But for this guy right here, because of the squaring, you're not going to be able to get a negative for your y values. In other words, if I plugged in a negative 1 for x, well, negative 1 squared is 1, 1 over 1 is 1. So now you get negative 1 comma 1. So that's the difference between the two. Now again, we just go back to the fact that it can't be 0 either, because if you plugged in a 0 right there for y, this equation has no solution. In order for 1 over x squared to be equal to 0, the numerator would have to be equal to 0, and the denominator would have to be non-zero. Well, in this case, the numerator is always going to be 1, so this equation has no solution. So the range here is going to be the set of all y such that y is greater than 0. When we look at this f of x, or again, you could say y is equal to 1 over x squared, it increases on the interval. So here it's going to be anything less than 0. Again, coming back, so that's this piece of the graph right here. So when we're less than 0 in terms of the x values, we're increasing as we go from left to right. This guy right here, you're going to be decreasing. So this is anything greater than 0 in terms of the x values. So you're decreasing for that branch right there. So I have that f of x equals 1 over x squared, decreases on the interval. So this is anything greater than 0. The graph is discontinuous at x equals 0. And then the line x equals 0, or the y-axis, is a vertical asymptote. Now this one, the line y equals 0, or the x-axis, is a horizontal asymptote. Again, just coming back up here. Think about what's happening to the y values as the x values approach either positive infinity or negative infinity. What's happening is your y values are getting closer and closer to 0. Just think about this as y equals, again, 1 over x squared. Think about some really large number that you plug in there. So let's just say you take 10 or something like that. So 1 over 10 squared is 100, so that's 1 over 100, and that's going to be 0.01. Well, if I keep increasing the value for x, again, as I approach positive infinity, what's going to happen is your y value is going to get closer and closer to 0. It's never actually going to get there, but it's going to get closer and closer. So that's going to give me this horizontal asymptote, which is y equals 0, or again, this is going to be the x-axis. So the vertical asymptote of x equals 0 and the horizontal asymptote of y equals 0, that's exactly the same as when we looked at y equals 1 over x. Then lastly, we have f of x equals 1 over x squared as an even function. So again, we already know that the graph is symmetric with respect to the y-axis. All right, so like I said before, at the beginning of this section on graphing rational functions, you're going to get easier problems where you could sketch the graph using graphing transformations. So if we have something like g of x is equal to 2 over the quantity 1/2 x minus 1 squared, and then minus 1, you can graph that based on this f of x equals 1 over x squared. So as I talked about in the lesson on graphing transformations, if your coefficient of x is not 1, you can go ahead and factor that out. You don't have to, but if you do it, it's going to make it a lot easier. So I'm going to write this as g of x is equal to 2 over. So now we have the brackets here, again, for us to factor out the 1/2. So you pull that out, you have 1/2 times the quantity x minus 2, and then this whole thing is squared, and then you have this minus 1. So what I would do is write this in terms of f of x. So we would have g of x here is equal to, well, you have this 2, that's going to multiply your function here. So f of, again, think about what's being plugged in for x. You have this guy right here that's being squared. Well, what's being squared here? Well, it's going to be this right here. So this right here will get plugged in right there. So you're just going to copy that. So this is going to be 1/2 times the quantity x minus 2. Close all that down. And then you just have this minus 1 on the outside. So when you write it like this, it makes it easy to think about all the graphing transformations we're going to apply. Remember, you have to be very specific about the order. Vertical transformations and horizontal transformations do not impact each other, so those could be done in any order. But when you're talking about vertical transformations, they have to follow the order of operations. So in this case, you're going to multiply by 2 first and then subtract away 1 second. When you talk about the horizontal transformations, those have to go in the reverse of the order of operations because you're undoing things. When you undo stuff, you go in the reverse order. So here you're going to end up multiplying by 2 first to undo this, and then adding 2 second to undo this. Like I talked about in the lesson on graphing transformations, when it's in factored form, you could just work left to right. That's why I spend the time to factor. So you could do this first, and then this one would be second, this would be third, and then this would be fourth. So the first thing we have is this multiplication by 2. Again, if it's a vertical transformation, it's very straightforward. So this gives me a vertical stretch by a factor of 2. Then when we come on the inside, again, for horizontal transformations, we're undoing things. So how do I undo multiplication by a half? I need to multiply by 2. So that gives me a horizontal stretch by a factor of 2. Then coming on the inside here, I have x minus 2. So to undo subtraction of 2, I want to add 2, so that's going to shift me to the right by 2 units. Then coming to the outside here, again, this is going to be straightforward because it's a vertical transformation. We have this minus 1 here. That's just going to shift me down by 1 unit. So if you have an x comma y on your graph, f of x equals 1 over x squared, when you get to your g of x, this is going to be 2x plus 2. Again, that's coming from this horizontal stretch by a factor of 2 done first, and then plus 2, that's coming from shifting right by 2 units. So 2x plus 2, and then comma, you have 2y minus 1. That's coming from the vertical stretch by a factor of 2. Again, that's done first, and then shifting down by 1 unit, that's done second. All right, so again, you can pause the video and do these on your own. I've pre-written this to make it a little bit faster. You have this negative 2 comma 0.25, which is going to go to negative 2 comma negative 0.5. You have negative 1 comma 1, which is going to go to 0 comma 1. You have negative 0.5 comma 4, which is going to go to 1 comma 7. You have 2 comma 0.25, which is going to go to 6 comma negative 0.5. 1 comma 1, which is going to go to 4 comma 1, and then 0.5 comma 4, which is going to go to 3 comma 7. All right, so looking at the graph, this is going to be for, again, g of x is equal to 2 over the quantity 1/2 x minus 1 squared. And then we have this minus 1 here. You see the points that I just talked about. So for this piece of the graph right here, you have negative 2 comma negative 0.5, you have 0 comma 1, and 1 comma 7. For this piece right here, you have 3 comma 7, you have 4 comma 1, and 6 comma negative 0.5. Now, you can get more points if you need them, but I think that's enough to get a good sketch going. You need to know this vertical asymptote is x equals 2, and this horizontal asymptote is y equals negative 1. Again, how do we figure that out? Well, essentially, you're just looking at your shifts. For the vertical asymptote, again, it's normally x equals 0 or the y-axis. What was the horizontal shift? Remember, we shifted right by 2 units, and we're going to see the vertical shift is down by 1 unit. So coming back, because we had a horizontal shift to the right by 2 units, instead of this being x equals 0, now it's going to be x equals 2 for the vertical asymptote. Instead of it being y equals 0, or the x-axis for the horizontal asymptote, the shift was 1 unit down, so now we get y equals negative 1. So if you have your vertical asymptote and your horizontal asymptote, you're good to go. When you sketch this graph, it's going to approach but not touch the vertical asymptote. So that's this right here and this right here. And then this is drawn to where it approaches but does not touch your horizontal asymptote there and there. And I know when you look at these graphs drawn by a computer, or even when you hand draw them, it's going to look like it's touching, but again, it's getting very close but not touching. That's why we have our asymptote there drawn as a dashed line, so you know that. All right, as we continue to work through this section, we're going to see harder examples that we can't graph using graphing transformations. So for those type of problems, you need a general procedure that you can use for graphing a rational function. So in order to work our way up to that procedure, we need to understand asymptotes and how to find asymptotes. And I'm just going to start with vertical asymptotes. So the line x equals a is a vertical asymptote of the function y equals f of x if y approaches positive or negative infinity as x approaches a. This is from the right or left. In other words, what we're saying is that if the absolute value of f of x, or you could say the absolute value of y, approaches positive infinity as x approaches a, again, this would be from the right or the left, then the line x equals a is a vertical asymptote. Now, again, when you read definitions like this, a lot of times it's not crystal clear until you start seeing examples. You can just relate this back to what we saw earlier. We had f of x is equal to 1 over x, and just think about it this way. So we already know that there's a vertical asymptote that is going to be x is equal to 0, and that's created because you cannot plug in a 0 for x. Division by 0 is undefined. But again, just using this approach here, we can say that the line x equals 0 is a vertical asymptote because y approaches negative infinity as x approaches 0 from the left. And then y approaches positive infinity as x approaches 0 from the right. So you can write it like this. You can also use this right here, which we saw earlier, if you want to combine things. So the absolute value of y is going to approach positive infinity as x approaches 0. Again, when you use this without the plus or minus up here, this means, again, like we said earlier, from the right or left. So just matching things up, this tells us that we would have a vertical asymptote at x equals 0. So we're just using that definition here. So a rational function can have 0, 1, or more than one vertical asymptotes. Then the graph of a rational function can never intersect a vertical asymptote. That's because the vertical asymptotes are being created because of division by 0. So at those x values, the function will be undefined, so you're never going to be able to intersect where you have a vertical asymptote. All right, so we're going to look at some summary images real quick. So this is for y approaches positive infinity as x approaches a from the right. So this right here is an x value of a, and you can see that as the x values get closer and closer to a, again coming from the right, the y values are increasing without bound or approaching positive infinity. Then over here, y approaches positive infinity as x approaches a from the left. So this right here, again, we're approaching an x value of a from the left. The y values are again increasing without bound or approaching positive infinity. Then similarly, we have y approaches negative infinity as x approaches a from the right. Again, this is an x value of a. As the x values get closer and closer to a coming from the right, the y values decrease without bound or approach negative infinity. Then on this one, we have y approaches negative infinity as x approaches a from the left. So as the x values are getting closer and closer to a, again coming from the left, now the y values are decreasing without bound or approaching negative infinity. All right, let's talk about a horizontal asymptote now. So something like the line y equals b is a horizontal asymptote of the function y equals f of x if y approaches b as x approaches positive or negative infinity. So in other words, if f of x, or again you could say y, approaches b as the absolute value of x approaches positive infinity, then the line y equals b is a horizontal asymptote. So again, just like we did before, we can go back to the f of x is equal to 1 over x that we already know. This one has a horizontal asymptote, which is y equals 0. So again, using this definition and matching things up, your b value here is going to be 0 because we're saying that y approaches 0 as x approaches positive infinity. And then also y approaches 0 as x approaches negative infinity. Again, just matching it up with this definition. You can even use this one, which is a little bit easier to write. So you can put that y approaches 0 as, and you could just use absolute value here to make it into one statement. So the absolute value of x approaches positive infinity. Let me fix that symbol there. So matching things up, we can say our y equals 0 is a horizontal asymptote for our f of x equals 1 over x. Now, when we talk about a rational function, it can have at most one horizontal asymptote. When we talk about vertical asymptotes, you can have as many of those as you like. There's no limit. But with non-vertical asymptotes, so I'm talking about a horizontal asymptote, or what we're going to talk about later on, which is a slant asymptote, you can have at most one of those. You might have 0, but if you have one, it's only going to be 1. Then this one, the graph of a rational function can intersect a horizontal asymptote. So with a vertical asymptote, the graph can never intersect that. Your graph can't have a point there because that x value makes the function undefined. But with a horizontal asymptote, we're not going to see that because what we're thinking about is what happens to the y values as x gets really, really large, approaches positive infinity, or as x approaches negative infinity. So it's okay if it intersects the horizontal asymptote, as we'll see with some examples coming up. All right, so just to get a little visualization of what this could look like. So this is y approaches b as x approaches positive infinity. So again, as the x values increase without bound, so as we approach positive infinity, the y values are approaching a value of b. Then over here, y approaches b as x approaches negative infinity. So here we're talking about as x decreases without bound. So as we approach negative infinity, again, the y values are approaching b. All right, in terms of finding asymptotes, it's actually pretty simple overall. So for vertical asymptotes, I have here, we can find the vertical asymptotes by finding the values for x that make the denominator 0. So it's the same process as you would use for finding the domain. Take your denominator, set it equal to 0, and solve. The solutions to that equation, you're going to have x equals whatever the solution is or the solutions. Those are going to be your vertical asymptotes. For horizontal asymptotes, we need to think about what happens to our y values as x approaches positive or negative infinity. So this is a model you would see in your textbook. Essentially, the only thing you really need to pay attention to is the leading term here and the leading term here. You can forget about the rest of the stuff. It's not going to come up. Essentially, you have a sub n, x to the power of n. That's the leading term in the numerator. And then b sub m, x to the power of m. That's the leading term in the denominator. So that's what you want to make sure you understand. So n is the degree of the numerator and m is the degree of the denominator. So for the vertical asymptotes, again, if a is a 0 of the denominator, then the line x equals a is a vertical asymptote. So that's very straightforward. Take your denominator, set it equal to 0, and solve. That's how you're going to find your vertical asymptotes. Then for horizontal asymptotes, you have these three different situations. So first, if n is less than m, then there is a horizontal asymptote y equals 0 or the x-axis. So it's just that simple. In other words, what we're saying is that if the numerator has a lower degree than the denominator. So again, when we say n is less than m, n is the degree of the numerator, m is the degree of the denominator. Then this scenario here is if n is equal to m. So in that case, then there's going to be a horizontal asymptote, which is y equals a sub n over b sub m. Okay, so it's the ratio of the leading coefficients. So this guy over this guy. And you'll see an example of that and where that's coming from. So in other words, I have here, if the numerator and denominator have the same degree, y equals the ratio of the leading coefficients is the horizontal asymptote. Then lastly, if n is greater than m, then there won't be a horizontal asymptote. So in other words, if the numerator has a greater degree than the denominator, you just won't have a horizontal asymptote. You could have something called a slant asymptote or an oblique asymptote, and that's when the degree in the numerator is exactly one more than the degree in the denominator. And I'll give you an example of that here momentarily. All right, let's look at some examples. So we're just going to find the asymptotes. So f of x equals x minus 3 over x squared plus x minus 2. So if I want to find the vertical asymptotes, what would I do? I would take this denominator here, I would set it equal to 0, and I would solve. So coming down here, you have x squared plus x minus 2 equals 0. We can factor this as the quantity x minus 1 times the quantity x plus 2. So again, set that equal to 0. And then using the zero product property, you get this factor x minus 1, set that equal to 0, or this factor x plus 2, set that equal to 0. So the solutions would be x equals 1, or negative 2. So coming back up, you would have a vertical asymptote, which is x equals 1. And then you would also have one, I'll just put a comma, you'd also have one at x equals negative 2. Then thinking about the horizontal asymptote, would we have one? Well, the degree of the numerator is going to be 1. The degree of the denominator is going to be 2. Let me just circle this and circle this. So the degree of the numerator is less than the degree of the denominator. That tells us that the horizontal asymptote is going to be y is equal to 0. So that's pretty simple overall. Now let me show you a way that you can think about this. So this is something you would see in a pre-calculus textbook when they're explaining the concept. So what you're going to do is you're going to take the highest power, which in this case is x squared, and so you're going to divide everything by that highest power. So the way you can do that is you can multiply by 1 over x squared over 1 over x squared. Remember that this guy is equal to 1 as long as x is not 0. One thing about doing this technique, if you look at this guy right here, the original guy, it is defined where x is 0, but this guy right here that we're going to change this into is not defined where x is 0. That actually doesn't matter for our purposes here because we're only going to think about what happens to x as it goes to positive infinity or negative infinity. We're not really concerned with what happens when it's 0, so this is okay. So we're going to multiply this by, again, 1 over x squared over 1 over x squared. We go through the simplification and we get this. So if I think about what happens to this guy right here as x approaches, let's just do positive infinity, or you could do negative infinity, doesn't matter. It's going to be the same thing. Well, this guy right here is going to go to 0. This is going to go to 0. This is going to go to 0. And this is going to go to 0. So what would I have left in that case? If this is 0 minus 0, you would have 0. And then if this is 0 and this is 0, you have 1 plus 0 minus 0. Well, that's 1. 0 over 1 is equal to 0. 0 divided by any non-zero number is equal to 0. So that means that as x approaches positive infinity or negative infinity, this guy is going to approach 0 over 1, which is 0. That means that the line y equals 0 is your horizontal asymptote. Again, that's the long way to do it. You don't need to do it that way. Just remember the rule that if the numerator has a lower degree than the denominator, you automatically have a horizontal asymptote, which is y equals 0 or the x-axis. All right, let's just verify what we found using a graph. Again, I left you a link for this on Desmos. So this is going to be for f of x equals x minus 3 over x squared plus x minus 2. So first we have this vertical asymptote of x equals negative 2. And we can just use this as an example to think about our definition of a vertical asymptote. First off, we know that this is created because if you plugged in a negative 2 for x in this function, you would get division by 0, which is undefined. So that's why you get this guy right here. Additionally, if we think about what's happening to the y values as x approaches negative 2 from the left, well, this guy is approaching negative infinity. So y approaches negative infinity as x approaches, this would be an x value of negative 2 from the left. So again, as we get closer and closer to an x value of negative 2, coming from the left, the y values are approaching negative infinity, or you could say we're decreasing without bound. Then additionally, y approaches positive infinity as x approaches negative 2 from the right. So as I'm approaching an x value of negative 2, again, coming from the right, I am increasing without bound, or the y values are approaching positive infinity. So following the definition of a vertical asymptote, that tells me that I have a vertical asymptote at x equals negative 2. Now you could use a similar thought process for this guy right here, which is the other one we found, which was x equals positive 1. So that's also a vertical asymptote for us. Now additionally, we're going to have a horizontal asymptote, which in this case is going to be the x-axis, or the line y equals 0. So for this part of the graph right here, you can see that as the x values decrease without bound, so as they approach negative infinity, the y values get closer and closer to 0, but they don't get there. Then for this piece right here, you're going to notice that we actually cross over the x-axis. You have an x-intercept here, which is 3, 0. That's okay with a horizontal asymptote. Again, we're only thinking about what happens as x gets really, really large, so approaches positive infinity, or what happens as x approaches negative infinity. So even though this crosses over here, as you get really, really large in terms of the x values, the y values are getting really, really close to 0. So that's why y equals 0 is a horizontal asymptote. All right, let's look at another example. So here we have f of x equals 4x squared minus x minus 4. This is over 2x squared plus x plus 1. So let's start with the vertical asymptotes. So take the 2x squared plus x plus 1, set it equal to 0, and solve. And what you're going to find, again, you can use the quadratic formula for this, you get two non-real complex solutions. So you get x equals negative 1 plus or minus I times square root of 7 over 4. So if this happens, really when you think about the domain, it's all real numbers. There's no real number that I can plug in for x such that the denominator would be 0. And when we think about the domain, it's all real numbers except those that make the denominator 0. Well, there are no real numbers that make the denominator 0, so it's all real numbers. So when something like this happens, you would say that there's none. You don't have a vertical asymptote because you can plug in any real number that you want. You're not going to get division by 0. If you want to guard against this and you want to go more quickly, you don't have to actually go through and get the zeros in this case. Again, if you notice that the discriminant, which is b squared minus 4ac, is negative, you know you have two non-real complex solutions, and you could just stop and say, I'm not going to have any vertical asymptotes. So if you plug in, again, a is 2, b is 1, c is 1, to this part right here, you would get x equals negative 1 plus or minus the square root of 1 squared minus 4 times 2 times 1 over 2 times 2. Well, if you go through and simplify, now you have x equals negative 1 plus or minus the square root of 1 minus 8 over 4. Well, this right here is going to turn into negative 7 right there, and you could just stop. You know that you're going to end up with two non-real complex solutions. Again, as we talked about earlier, it's x equals negative 1 plus or minus I times square root of 7 over 4. Now let's talk about the horizontal asymptote. And in this case, the degree of the numerator, which is 2, is exactly the same as the degree of the denominator, which is also 2. So in this particular situation, you want to take the ratio of the leading coefficients. So in other words, 4 over 2. So y equals 4 over 2, which is equal to 2. So y equals 2 is the horizontal asymptote. Again, that's the quick way to do it. If you want the long way, again, we're going to use our trick where we're going to take the highest power of x, which is x squared. And so we're going to multiply this by 1 over x squared over 1 over x squared. And that's just going to be used, again, so we can think about things. Well, what happens as x approaches positive infinity, so it gets really, really big, or negative infinity? So you can think about, well, this guy right here, this 1 over x is going to go to 0, 4 over x squared is going to go to 0, 1 over x is going to go to 0, and 1 over x squared is going to go to 0. So what are you going to be left with? You're going to be left with 4 over 2, right, which is the ratio of the leading coefficients. So as x approaches positive infinity or x approaches negative infinity, your y values are getting closer and closer to 2. So just coming down to the graph to verify this, again, this is the f of x equals 4x squared minus x minus 4 over 2x squared plus x plus 1. You'll notice that you don't have any vertical asymptotes, again, because this guy right here, if you set it equal to 0 and solve, you get two non-real complex solutions. So there's no real number I can plug in for x such that the denominator would be 0. And so again, you're not getting a vertical asymptote in that situation. In terms of the horizontal asymptote, again, it's y equals 2. So it's this line right here. So you'll see that as x increases without bound, as it approaches positive infinity, we're getting closer and closer to a y value of 2. And then over here, we actually cross through this line y equals 2, and that's okay. You can do that with a horizontal asymptote. You have this point negative 2 comma 2 where that happens. And again, as you think about the x values approaching negative infinity, well, the y values now are approaching 2. So that's why we get our horizontal asymptote, which is y equals 2. All right, let's take a look at another problem. So here we have f of x equals 2x squared minus 5x plus 4 over x minus 1. So in this case, for the vertical asymptote, it's going to be real simple. You're just going to take x minus 1, set that equal to 0 and solve. And of course, you just add 1 to both sides. You get x equals 1. So let's put x is equal to 1. For the horizontal asymptote, this degree right here in the numerator, that's going to be a 2, is greater than the degree in the denominator, which is going to be a 1. When that happens, you will not have a horizontal asymptote. You can just say that there's none. When it's exactly one more, you're going to have a slant asymptote. So I'm going to show you that in a moment. For right now, let me just show you why we can say there's no horizontal asymptote. Again, just using the same thought process. So we start with this guy right here. And again, the highest power of x is x squared. So we use our trick. We're going to multiply by 1 over x squared over 1 over x squared. Again, we're just using this to think about what happens as x approaches positive infinity or negative infinity. Well, we can see that this guy right here is going to go to 0. This one would, and this one would. Okay, well, that's a problem for us because as x approaches positive infinity or negative infinity, what we're getting is 2 over 0, which is undefined. So what you can say is that y does not approach any real number as the absolute value of x goes to infinity. We will not have a horizontal asymptote in this situation. So this is going to occur when the degree of the numerator is greater than the degree of the denominator. If you look at the graph, you can verify this. This is f of x equals 2x squared minus 5x plus 4 over x minus 1. So you do have this vertical asymptote, which is x equals 1. So we have that guy right there. But you see that you don't have a horizontal asymptote. Now, you'll notice that I have another asymptote here, which is the line y equals 2x minus 3. I'm going to talk about where this is coming from in a moment. This is called a slant asymptote. Some people also refer to this as an oblique asymptote, but I'm just going to call it a slant asymptote. So for a slant asymptote, we previously stated that when the degree of the numerator is greater than the degree of the denominator, we will not have a horizontal asymptote. If, however, the degree of the numerator is exactly one more, and that's the case we have here, in our example, the degree of the numerator is 2, the degree of the denominator is 1, so then the degree of the denominator, then there will be a slant or oblique asymptote. Now, the way you get this in this situation is with some long division. In this particular case, we can use synthetic division because the denominator or the divisor here is of the form x minus k. So we can just take this 1 as the k value. Again, so you write that right here, and then you take 2, negative 5, and 4, and you can set up your synthetic division. So you drop this down. So 1 times 2 is 2, negative 5 plus 2 is negative 3, 1 times negative 3 is negative 3, 4 plus negative 3 is 1. So this right here is going to be the coefficient, again, dropping this by 1 degree. If this is squared, then this becomes to the first power. So you get 2x minus 3, and then plus this 1 right here is the remainder, and you put that over your divisor. So 2x minus 3, and then plus 1 over x minus 1. So looking at this, you can think about, well, what happens, just think about it in this form right here, what happens as x goes to positive infinity or negative infinity? Well, this piece right here is going to go to 0 because 1 over x minus 1, if x gets really, really large, you have 1 over some really, really big number, and that's going to go to 0. And the same thing would be true if x approached negative infinity. So this is going to approach 0. So what you're left with when that happens is just the 2x minus 3 part. And that's why when you come back to the graph, you see you have this slant asymptote, which is y equals 2x minus 3. All right, let's talk about holes in your graph. Some people call these removable discontinuities. So up to this point, we've only seen rational functions that were reduced to lowest terms, or you could say simplified. If we have a factor that can be canceled between the numerator and the denominator, we can do so, but only for values of x for which that common factor is not 0. Let me give you an example of this. So we have f of x equals 2x cubed minus 4x squared minus x plus 2 over x minus 2. So let me just factor the numerator. I'm going to put a little border here. We'll come back up in a moment. So if you have 2x cubed minus 4x squared minus x plus 2, well, from the first 2 right here, you could pull out a 2x squared. Inside, you're going to have x minus 2. From the second 2, you could pull out, let's just do negative 1. So inside, you would have x minus 2. So you'll notice that you have a common binomial factor of x minus 2. And so let's go ahead and pull that out. So that's going to come out here. So you're going to have this x minus 2 like that. Let me move this down a little bit. And then what's going to be left? You're going to have this 2x squared right there, and you're going to have this negative 1 right there. So we're going to have 2x squared and then minus 1 like that. Okay, let me get rid of all this. We're going to use this to rewrite things. So I'm going to say this is equal to, so I have the quantity x minus 2 times the quantity 2x squared minus 1. Okay, let me get rid of this. And actually, let me move this down. So this is over your x minus 2. So it's obvious at this point that you can cancel this with this. But there's an issue with this, and again, we talked about this earlier on in the course. When you think about what's going to be produced here, you're going to get 2x squared minus 1. So this function and this function are the same, except for where x is 2. Because if you look at this original rational function here, x can't be 2. If you plug in a 2 here, 2 minus 2 is 0. Division by 0 is undefined. If you plug in a 2 here, it's actually okay. 2 squared is 4. 4 times 2 is 8. 8 minus 1 is 7. There's no issue. So what you have to make sure you do is carry over any restrictions from the original rational function that are not in the new one that you create from simplifying. So the way you do that is you're going to put a little comma and you're going to say for x is not equal to positive 2. So you're carrying that over. So when you sketch the graph of this guy, you're going to graph f of x equals 2x squared minus 1, but where x would be equal to 2, you're going to put a hole. So that's going to look like this. This is f of x equals 2x squared minus 1, where x is not equal to 2. So this guy, if you look at where x is 2, you see that we put a little hole in the graph. So that would be 2 comma 7 on the normal graph for just f of x equals 2x squared minus 1. But on this graph, again, because of where it came from and because of the fact that we have to carry that restriction over, you're going to put a hole in the graph to say, hey, it's not going to be defined here. I gave you a link for this on Desmos. If you click on that link, you're going to need to take your mouse and actually put it directly over where the x value is 2, and then it's going to show you that 2 comma undefined there. If you don't mouse over it, you won't see it. So it's not obvious unless you take that step. All right, before we get to the procedure on graphing a rational function, we need 2 additional pieces of information. So the first thing is going to be the behavior of graphs of rational functions near vertical asymptotes. So we're going to let f of x be a rational function that is defined by a rational expression in lowest terms. That's actually important here. That means that this guy is simplified. So in other words, we cannot cancel a common factor between the numerator and the denominator. So we're not going to have a hole in this situation. So if n, which will be our exponent, is the largest positive integer such that, again, you have this x minus a, this is a quantity raised to the nth power. Again, this is going to be a factor of the denominator of your f of x. So the graph of our rational function will look different based on whether the n value is even or odd. And we've actually seen this already, because if you think about something like f of x equals 1 over x squared, it looks like this guy on the left. And if you went to Desmos and you typed in f of x equals negative 1 over x squared, you're going to get what looks like this guy on the right. So what we're saying is that basically, if you have a vertical asymptote, let's just say it's x equals a in this particular case. Well, if what led to that was a factor, so in the denominator, x minus a, let's just say it's quantity squared, or it could be to the 4th power, 6th power. If it's even, well, you could have this scenario or this scenario. Again, this is going to be based on the entire function, but let's just keep it simple and say, as you approach a from either the left or the right, what's going to happen is the y values are approaching positive infinity. That's because there's no sign change from one side of this guy to the other side of this guy. And I'll explain with a full example in a moment. You could also have this situation right here. Now, let's say your n value is odd. Again, we saw this with f of x equals 1 over x. Well, now you do have a sign change from one side of this guy to the other side. So as we approach the x value of a from the left, here you're approaching negative infinity. As you're approaching x value of a from the right, well, now you're approaching positive infinity. Over here, you could have this scenario as well. So as you're approaching x value of a from the left, we're approaching positive infinity. As you're approaching x value of a from the right, now you're approaching negative infinity. So this is when n is odd. All right, let's look at an example. So here we have f of x equals 1 over the quantity x minus 3 squared. So you notice we have our vertical asymptote here, which is x equals 3. So where does that come from? Again, you take your denominator, which in this case is x minus 3, quantity squared. You set that equal to 0, and you solve. So I think we all know the solution there is x equals 3. But again, you could just say x minus 3 here is equal to 0. You add 3 to both sides of the equation. And so this is going to cancel and you get x is equal to 3. So that's what produces this vertical asymptote here, because obviously if you plug in a 3 here, 3 minus 3 is 0, 0 squared is 0, 1 over 0 is undefined. Now get rid of this. And I want you to think about the fact that on this side of your line, x equals 3, and on this side of your line, x equals 3, there's not a sign change. In other words, you can say that y approaches positive infinity as x approaches 3 from the left, and then also y approaches positive infinity as x approaches 3 from the right. And you can really combine that and just say y approaches infinity as x approaches 3 from either the right or the left. It would not matter. So the behavior is coming from the fact that you have something that is raised to an even power here. Because if I plug in something on this side of the line x equals 3, well, really this down here, before I square it, would be negative. So if I plugged in, let's say, a 2, you would have 1 over, you would have 2 minus 3 like that, quantity squared. So this would be 1 over. This would be 2 minus 3, that's negative 1. this would be -1 squared. But the fact that I'm squaring a negative makes it a positive, so I get 1 over 1. So I end up with 2 comma positive 1. If I had something like f of x equals 1 over just x minus 3, well, now that point would be down here. And what would end up happening is you would have something that looks like that. So you'd have this and then this. But in this case, because it's squared, it's flipping that up here. So you have this going this way and this going this way. So that's really important to understand, because when we graph stuff, you want to look at this guy right here, which is the exponent, and see if it's going to be odd or even. In the case where it's even, you're going to get something like this. So now I have f of x equals 1 over, and I did x minus 3 quantity cubed. But again, if you did x minus 3, you could just say to the first power, it's going to be the same thing generally, where this guy goes like this and this guy goes like this, because now you have a sign change on one side of this guy to the other. So here again is your x equals 3. That's your vertical asymptote. And now if you plugged in a 2, where you're going to get a -1. So 1 over, let's say 2 minus 3, and this is quantity cubed. Well, this equals 1 over, you're going to have -1 cubed. And now this is going to stay negative. -1 cubed is still -1. So you get 1 over -1, which is -1. So this guy is down here now. So for this one, y goes to or approaches negative infinity as x approaches 3 from the left. So as we're coming from the left. Then y approaches positive infinity as x approaches 3 from the right. Again, this is because this is odd and you have a sign change on one side of the sky to the other side of the sky. All right, let's think about the final piece of the puzzle here. So we have the behavior of graphs of rational functions near the zeros of the numerator. So I want you to recall from our lesson on graphing polynomial functions that the behavior of the graph of a polynomial function near one of its zeros will depend on whether the multiplicity of the zero is even or odd. So again, you can go back to that lesson if you want more detail. In the case where the multiplicity of the zero is even, we saw the graph would touch the x-axis and turn around. That's because there's no sign change on one side of that guy to the other side of that guy. In the case where the multiplicity of the zero is odd, we saw the graph would cross through the x-axis. That's because there is a sign change on one side of that guy to the other side of that guy. So the same concept will apply when graphing a rational function. So let f of x be a rational function that is defined by a rational expression in lowest terms, or again, we could say simplified. This means that we will not have a common factor that we can cancel between the numerator and denominator. So you won't have to worry about having a hole in the graph. If n, which will be our exponent, is the largest positive integer such that you have this x minus k quantity raised to the power of n, if that is a factor of the numerator of f of x, the graph of our rational function will look different based on whether the n value is even or odd. All right, so let's look at two examples of this, just so it makes sense, and when you're graphing, you'll know what to do. Essentially, you're going to look at this f of x equals the quantity x minus 3 squared over x minus 2, just using a little table. The way you set up your table is you think about what are your vertical asymptotes. In this case, you just have one, so one vertical asymptote. And then what are your x-intercepts? In this case, you just have one x-intercept. So how do you get the vertical asymptotes? You set the denominator equal to 0, and you solve. In this case, you have x minus 2. Set that equal to 0, you get x equals 2, so you get a vertical asymptote here, which is x is equal to 2. Then for the x-intercepts, you take your numerator, you set that equal to 0, and you solve. So you have x minus 3 quantity squared equals 0. You solve that, you get x equals 3. So that's why you're going to have this 3 comma 0 here. Now, because the multiplicity of this guy is going to be 2, right, because the exponent there is 2, what's going to end up happening is you're not going to have a sign change on this side of this guy to this side of this guy. So when your graph goes to this 3 comma 0, it's going to touch and then turn around. It's not going to cross through the x-axis. Let me get rid of all this highlighting and let's focus on this over here. So you'll notice that I have a little table and I have anything less than 2. So anything less than 2, anything between 2 and 3, and then anything greater than 3. So you'll notice for this guy up here in the numerator, x minus 3 quantity squared, you'll see positive, positive, and then positive. So where does that come from? That's the fact that this guy is squared. So again, no matter what I plug in there, unless it's 3, when I square it, I'm going to get something positive. Because if the result of this is negative, when I square it, I get a positive. If the result is positive, I keep a positive. If I plugged in a 3 there, 3 minus 3 is 0, 0 squared is 0, but that's only going to be for right there. Everywhere else, this guy is going to be positive. Now, for this guy right here, this x minus 2, that's pretty simple. You just say x minus 2, where is that less than 0? You add 2 to both sides of the inequality. This cancels. you get x is less than 2. So anywhere where x is less than 2, so this is x equals 2 right here. So if I'm to the left of that, well, the x minus 2 down here would be negative. And so you see that you have a negative right here, and then everywhere else it would be positive. So positive and then positive. Well, with a fraction, again, a positive over a negative, that's going to give you a negative. So you'll see that where we're less than 2, so to the left of this guy, the function values are negative. And so let me erase all this highlighting. I'm just going to highlight this. You'll see that your function here, the values are negative. You're below the x-axis. Then what happens is everywhere else, so between 2 and 3, and then anything greater than 3, the function values are positive because, again, you have a positive over a positive in each case. The only exception to that is when the x value is 3, that's going to give me a y value of 0 or a function value of 0. So this guy right here is going to be positive, positive, positive. We're going to go to an x value of 3. And so we're going to have a function value of 0. So we're going to be on the x-axis, or we're just going to touch, and then we're going to turn back around because the function values are going to be positive, positive, positive. So it's just something important to understand when you're graphing these guys to know the behavior of this, whether or not it's going to touch and turn around or go through. Now here's an example of where it would cross through because you will have a sign change from one side to the other. So now I have f of x equals x minus 3 over x minus 2. So you're going to have the same vertical asymptote here, which is x equals 2, and you're going to have the same x-intercept, which is 3, 0. So I have the same intervals here, so anything less than 2, between 2 and 3, and then anything greater than 3. But what's going to change is that this guy in the numerator, even though you set it equal to 0, x minus 3 set that equal to 0, and you solve, you still get x equals 3. The multiplicity of that 0 is 1, which is odd. So if you look at this, x minus 3, let me just set this up. Where is that less than 0? You add 3 to both sides of the inequality there. This would cancel, you get x is less than 3. So in this interval and this interval, it's going to be negative, and then in this interval, where we're greater than 3, it'll finally be positive. In terms of x minus 2, we already know that that's negative in this interval, and then positive in this one and this one. So now, where x is less than 2, we have a negative over a negative, which gives us a positive. Let me erase everything. So that's going to be where x is less than 2. You can see the function values are positive. So that's why we are above the x-axis. And then for this one, between 2 and 3, you're going to notice that you have a negative over a positive, which is negative. So that's going to be this piece right here. You would see that the function values are negative. We're below the x-axis. And then if you come to where we're greater than 3, you have a positive over a positive. Well, that's a positive. So notice that where x is greater than 3, the function values are positive, so we're above the x-axis. So notice that what's happening is you're coming from below the x-axis, and now you get to 3, 0, you're on the x-axis, and then after an x value of 3, or to the right of that, where you're crossing through, you're above the x-axis. So that's why this guy is going to cross through, because there's a sign change from this side to this side. Whereas with this one, there was no sign change, right? We were going to come down here, positive, positive, positive. We get to a y value of 0. We're going to touch here, and then we're going to turn around, positive, positive, positive. That's the difference between the two situations. All right, let's look at the procedure for graphing a rational function. So we have f of x is equal to p of x over q of x, where q of x, this guy in the denominator, is not 0. P of x and q of x are polynomials, and the rational expression is in lowest terms. So I'm going to highlight that because that's important. Remember, we talked about what would happen if we have to cancel and we have a hole in the graph. So that's not going to apply here. We're going to be looking at things that are already simplified or in lowest terms. So the first thing you want to do is find and sketch all asymptotes. The second thing is to find the x and y intercepts. We know that the y-intercept would occur at 0, f of 0, and the x-intercepts would occur at k, 0, where k is a 0 of the numerator. In other words, you're taking the numerator, setting it equal to 0, and solving. The solutions there would correspond to x-intercepts. Then for the third thing, we're going to determine whether the graph will intersect its non-vertical asymptote. So if it exists, a lot of times if you get a horizontal asymptote of y equals 0 or the x-axis, well, you don't need to do this because you've already figured out if you have an x-intercept. And so this would be already done for you. There's other scenarios. You might get a horizontal asymptote that's maybe y equals 2 or a slant asymptote, something like that. In that case, you'd have to take this additional step. Then the fourth thing is we want to split the number line up into intervals based on the x-intercepts and vertical asymptotes. We're going to pick an x value in each interval, then find and plot the related point. This right here where it says pick an x value, you might need to pick several. It's just depending on what you're trying to graph. Some graphs are more complex and they take more points. But for a basic rational function, something that's easy, you can just use one x value in each interval, and that would be okay. Then for 5, the last thing, we're going to just sketch the graph. All right, let's start off with f of x equals, we have x minus 1 over x squared minus 6x plus 8. The first thing I'm going to do is find the vertical asymptotes. Take the denominator, set it equal to 0, and solve. So if we factor this, we get the quantity x minus 4 times the quantity x minus 2, set that equal to 0, 0 product property, x minus 4 equals 0, or x minus 2 equals 0. We solve each one, you get x is equal to 2, or 4. So those would be your vertical asymptotes. Then in terms of your horizontal asymptote, in this case, I want you to notice that the degree of the numerator is 1. The degree of the denominator is 2. So what's the rule? If the degree of the numerator is less than the degree of the denominator, you will have a horizontal asymptote, which is the x-axis or the line y equals 0. Now, in terms of your x-intercept, because you're only going to have one here, you take your numerator, which is x minus 1, you set that equal to 0, and you solve. So you get x equals 1. So the x-intercept is going to occur at 1, 0. Then for your y-intercept, you're going to plug in a 0 for x. So f of 0, that would be equal to 0 minus 1 over 0 squared minus 6 times 0 plus 8. So if you simplify, this would be equal to negative 1 over 8. So your x-intercept occurs at 0, negative 1/8. All right, so I have everything summarized here. So you have a vertical asymptote, which is going to be x equals 2, then another that would be x equals 4. So this is your x equals 2, and this is your x equals 4. Okay, coming back, you have a horizontal asymptote, which is y equals 0. Now, I don't label an asymptote if it's the x-axis or the y-axis. You can if you want, so I'm not going to put anything there. But if you wanted to label this and just do something like y is equal to 0, and you could put horizontal asymptote on your page, that's fine. A lot of teachers will let you do that, or you can make a dashed line there, whatever you want to do. Okay, the x-intercept, we know that occurs at 1, 0, and the y-intercept occurs at 0, negative 1/8. So this is a little bit hard to see because of the font, but this right here is your 1, 0. That's going to be your x-intercept. And so that's also the point where we're going to intersect that horizontal asymptote. So again, when that happens, if you have an x-intercept like we do in this case, and you have a horizontal asymptote, which is the x-axis or the line y equals 0, you don't need that extra step like we talked about in the procedure. We already know it's going to cross through right there. Then the other guy was this one right here. So this is 0, negative 0.125. That's just negative 1/8 as a decimal. And then coming back, I have some additional points. I'll talk about those in a moment. So we split the number line up into intervals, again, using the vertical asymptotes and then the x-intercept. So you can have anything less than 1, you're going to have between 1 and 2, then between 2 and 4, and then anything greater than 4. So just pick an x value that's in the interval and plug it in and get the y value. I went ahead and grabbed some stuff that was easy to work with. A lot of times when you do this, you don't know what's easy to work with. So just plug it into your calculator, and if it's a nasty decimal, just round it to the nearest hundredth or the nearest thousandth. Whatever you want to do, you're just trying to get an idea of what this looks like. It does not have to be perfect, so do not worry about that. So this guy is going to be negative 2, negative 0.125. Then this guy is going to be 1.5, 0.4. This guy is going to be 3, negative 2. This guy is going to be 4.5, 2.8. So coming back, that's going to be these points. Let me just highlight them. So this is your negative 2, negative 0.125. Then this one is going to be your 1.5, 0.4. This one's going to be your 3, negative 2. And this one's going to be your 4.5, 2.8. Now, you're going to see that I listed, let me erase these, some additional points. So I put in 2.5, negative 2. That's going to be right there. And then I put in 6, 0.625. I just put those in to help. You don't need them, but sometimes with a shape like this, you want them. It just makes it a little bit more accurate. So you'll see I put those as additional points. So 2.5, negative 2, and then 6, 0.625. This one right here is probably the hardest thing to get. We have not taken calculus yet, so we don't know about derivatives and the first derivative test and all those different things. So finding the local maximum point, like I talked about with graphing polynomial functions, is a challenge. So you can actually do it and get somewhat close by just plugging things in. So you could plug in 2.5, 2.6, 2.7, 2.8, and just look at the y values that you're getting, and you can get close to this. It does not have to be perfect, but the idea is that you're going to have to turn. Now, putting things together, we know that this guy right here, this x equals 2, and this guy right here, this x equals 4, those came from zeros that had a multiplicity which was 1. So that's an odd multiplicity. So what does that tell me? When I look at this guy right here going up, that means this guy is going to be going down. And when I look at this guy right here going up, that means this guy right here is going to be going down. And that's the toughest part here is you know you're going to turn, but you just don't know where. And that's where that approximation comes in. Again, I've already given you this, the local maximum point. So 2.732, negative 1.866. That's an approximation, but it lets us know that we would turn somewhere like this. So something like that. And then this part right here, it's actually important to get right. We know that we're going to cross through the x-axis right here, because again, that 0 that's associated with that x-intercept has a multiplicity of 1. So we know we're crossing through right there. That means we're crossing through the x-axis or the horizontal asymptote, which is y equals 0. So it's going to go like that. It's going to come down, and then it's going to come back up, and it's going to keep getting closer and closer to 0 as we have x values that go out to negative infinity. And I know that's not drawn straight, but I'm just not a good drawer. Then this piece right here would just come down here. On this piece, it's not going to actually intersect the x-axis. It's just going to get closer and closer to it without touching. And I know I'm a bad drawer. Let me show you a computer-generated version, which is obviously much better. So you can see that this piece right here, it's coming down, and you can zoom in on Desmos, it's a little bit better. It's going to cross through here at 1, 0, and then what's going to happen is it's going to come down a little bit, and then it's going to start coming back up, and it's going to approach the x-axis, but it's not going to touch it, right? It already crossed through here, but once it crosses through, it does not touch it again. It's just going to keep getting closer and closer as we go that way. This piece right here, again, this goes down, comes up, makes its turn, goes back down, and then this piece right here, we're going down like this, and we're approaching the x-axis, but we're never actually going to touch it. All right, let's look at the next one. So here we have f of x equals x squared minus 4x plus 4 over x minus 1. So again, take the denominator, which is x minus 1, set it equal to 0, and solve. So you get x equals 1. That's your vertical asymptote. Take your numerator and set that equal to 0. We're doing that to get the x-intercept. So x squared minus 4x plus 4 equals 0. You can factor that. This is the perfect squared trinomial. That becomes the quantity x minus 2 squared equals 0. So if you solve that, you just get x is equal to 2. But keep in mind that this is squared, so the multiplicity of that 0 is 2. And so this x-intercept, which is 2, 0, we're going to touch and turn around there. For the y-intercept, plug in a 0 for x. So you get 0 squared minus 4 times 0 plus 4 over 0 minus 1. So this equals negative 4. So you're going to get 0, negative 4. Now, in terms of the horizontal asymptote, you are not going to have one because the degree in the numerator is 2 and the degree in the denominator is 1. So if the degree in the numerator is greater than the degree in the denominator, you will not have a horizontal asymptote. But if the degree in the numerator is exactly 1 more than the degree in the denominator, you will have a slant or oblique asymptote. Again, we know how to do this already. We set up some long division. So this coefficient is a 1. That's why you have a 1 there. This is negative 4, and then this is a 4. So 1, negative 4, and 4. This is in the form of x minus k. So your k here is 1, so that goes out here. Drop this down. 1 times 1 is 1. Negative 4 plus 1 is negative 3. 1 times negative 3 is negative 3. 4 plus negative 3 is 1. So you get 1 as the coefficient for x. Because again, if this is squared, this becomes to the first power. You drop it by 1 degree. Then you have minus 3 and then plus. This is your remainder, and that goes over the divisor or the denominator. So this becomes x minus 3 plus 1 over x minus 1. So remember from earlier, this is the part you're going to focus on. Because as x goes to positive infinity or negative infinity, this part right here is going to go to 0. So what's happening is you're getting closer and closer to that line, which is y equals x minus 3. So let me write everything out for you. We have a vertical asymptote, which is x equals 1. We have a slant asymptote, which is y equals x minus 3. We have an x-intercept, which is 2, 0. We're going to touch and turn around there. And then we have a y-intercept, which is 0, negative 4. I have split the number line up into some intervals. Again, anything less than 1, between 1 and 2, and then anything greater than 2. And I have some points. So negative 1, negative 4.5, 1.5, 0.5, and then 3, 0.5. So I'm going to plot these in a moment. I want to talk about something that's a little bit time consuming. So you heard me mention that if you had a horizontal asymptote and it was the line y equals 0 or the x-axis, if you find the x-intercept, you really don't have any more work to do there because you know what's going to happen in terms of if you're going to cross your horizontal asymptote or not. When you don't have that situation, then you have to do some work. So you're going to take your function here, so x squared minus 4x plus 4 over x minus 1, and you're going to set that equal to your slant asymptote, which was x minus 3. So keep in mind that you're trying to solve for the x value where those two y values or those two function values, you could say, would be equal. So to do this, you would multiply both sides by x minus 1. So you'd have x squared minus 4x plus 4 is equal to x minus 3 times x minus 1. All I did was I multiplied both sides by x minus 1. If you simplify over here just using FOIL, you're going to have x squared minus 4x plus 3, and then you'll notice that this would cancel away. You just subtract x squared away from each side. If you add 4x to both sides, that's going to cancel away. You're going to be left with 4 equals 3, which is a false statement. So we know that when this happens, you have an equation with no solution, so we will not intersect that slant asymptote. Okay, so just coming down and putting everything together on the graph, this is your negative 1, negative 4.5. This is your 0, negative 4. This is your 1.5, 0.5. This is your 2, 0. This is your 3, 0.5. This is your vertical asymptote, which is x equals 1. And then this is the slant one, which is y equals x minus 3. So pretty much this one's very easy to do. You know that right here, this is going to touch and turn around. So this would do something like this, like that. Touch and turn around like that. Again, as the x values go out to positive infinity, this is approaching that line y equals x minus 3, so that's how I know about this and this. When we think about the vertical asymptote here, which was x equals 1, that came from a 0 that had a multiplicity of 1. So I know that this guy right here is going to go like that because this one goes like that. And then this is going to turn here and then come back. And again, as x decreases without bound, this is going to approach the line y equals x minus 3. Again, we could just check the computer-generated version, which is a lot easier to see. So again, this guy right here is going to come down, touch, and turn around. Again, as x approaches positive infinity, this approaches that line y equals x minus 3. And then down here, you'll notice that again, because this is going up, this is going down here. So this is going to come, and it's going to turn here, and it's going to approach that line, which is y equals x minus 3, as x goes to negative infinity. All right, let's look at one more. So now we have f of x is equal to x minus 2 over x minus 3 quantity squared times x minus 1. So for the vertical asymptotes, you take your x minus 3 quantity squared times x minus 1, and you set that equal to 0. And you could just do x minus 3 equals 0. So the solution there is x equals 3. Or x minus 1 equals 0. The solution there is x equals 1. But notice that again, this is squared. So this right here, when you look at that vertical asymptote, you have to be very, very careful because you're going to have, let me just show you the graph. This is your x equals 3. Again, like we saw with y equals x squared, you have, let me actually erase this and show you, this guy right here, as x approaches 3 from the left, y is approaching positive infinity. And then as x approaches 3 from the right, y is approaching positive infinity. Again, that's because the multiplicity of that 0 was 2, and that's even, so that's what's creating that. There's not going to be a sign change on one side of that guy to the other side of that guy. So that's one of the most important things to understand with this, because if you don't get that, you might end up drawing this wrong. Coming back up here, let's get the x and y intercepts. So the x-intercept, again, you just take your numerator, x minus 2, set that equal to 0 and solve. You get x equals 2, so it's 2 comma 0. For the y-intercept, you just plug in a 0, so f of 0 is equal to 0 minus 2 over 0 minus 3 quantity squared times 0 minus 1. So if you simplify this, you're going to get this is equal to 2/9. So 0 comma 2/9. And just putting everything together, you have a vertical asymptote, which is x equals 1, and then also x equals 3. Again, this one right here is the one you want to put a star next to or something like that, just saying that the multiplicity of that 0 was 2. It's even, so it's going to have a different behavior than the other one. The horizontal asymptote is y equals 0, and that's because the degree of the numerator is less than the degree of the denominator. Then the x-intercept is 2 comma 0, the y-intercept is 0 comma 2/9. Again, splitting up the number line into intervals, you have anything less than 1, anything between 1 and 2, between 2 and 3, and then anything greater than 3. These are just things that I picked out. Again, if you're picking something or you're working with decimals, don't worry about if you get something that's nasty, just round it and move on. So I have 1/2 comma 12 over 25. I have 3/2 comma negative 4/9. I have 5/2 comma 4/3, and then 4 comma 2/3. Okay, putting everything together, here's your 0 comma 2/9. Here's your 1/2 comma 12 over 25. This is your 3/2 comma negative 4/9. This is your 2 comma 0. This is your 5/2 comma 4/3, and then this is your 4 comma 2/3. So again, I know with this guy right here, the multiplicity was even. So that tells me this is going to go up like this, and then this is also going to go up like this. And so I can draw this. I know that the horizontal asymptote is going to be this guy right here, so it's going to approach the x-axis but not touch it. Again, because the x-axis or the line y equals 0 was the horizontal asymptote, we already know it's going to intersect right here at 2 comma 0, but it's not going to intersect anywhere else. Now, in terms of this one, again, this multiplicity of this was odd. So that means that if this guy is coming up like this guy is going to go down like this. So then you can just connect this like that, and this piece right here becomes going down like this, and again, approaching the x-axis but not touching. Again, looking at the computer-generated version, you're going to have this piece right here, again, coming down, approaching the x-axis but not touching. This right here is going to look like this. Again, this is where we're going to cross through the x-axis. Remember that the multiplicity of that 0, when we got 2 comma 0, that's 1, so that's why we're going to cross through. And then this right here is going to approach this way, and this is going to approach this way, and then this guy right here is going to come down and approach the x-axis but not touch it. In this lesson, we want to learn about solving polynomial inequalities. All right, so previously we talked about how to solve quadratic inequalities. If you remember how to do that, the process for solving polynomial inequalities is exactly the same. It's just that in this section, you're going to be dealing with some polynomial functions that are of degree 3 or higher, whereas in the section where you dealt with quadratic inequalities, all of the polynomial functions you dealt with were of degree 2. So this is just going to be a lot more tedious. So I have here for the procedure, we're going to rewrite the inequality, so the right side is 0. So the problems I'm going to give to you, and also in a lot of books, they're factored. So this really isn't as much of an issue as when we dealt with quadratic inequalities. But if it's not given to you in factored form, just move all your terms to one side of the inequality. So let's just say the left side, we're going to call that f of x. That's going to be our polynomial function we're dealing with. And then the right side should be 0. So this less than here will have f of x is less than 0. I have the less than can be replaced with the appropriate inequality symbol. So it might be greater than, less than or equal to, or greater than or equal to, just depending on what you get in your problem. Then I have to replace the inequality symbol with an equality symbol, and then we're going to solve the resulting equation. So we're solving the equation. F of x, again, that's the polynomial function that we set up, is equal to 0. So the solutions to the above equation are known as the zeros. So we've talked a lot about that in this section. We know that the real zeros to the above equation correspond to x-intercepts on the graph. This right here is extremely important to understand for this section. Then we have here that the non-real complex zeros, because you can get those as well, will not, okay, let me read that again, will not correspond to x-intercepts on the graph. Let me come down here and read the rest. I have used the real zeros to create intervals on the number line. So in other words, you can make a number line, and I've already pre-drawn everything here, but just draw a horizontal number line. You can label it as the x-axis, and you're going to think about, well, those real zeros are going to give me my x-intercepts. You can mark those off and say, well, now I can use that to create intervals on the number line. And once you have those intervals, you can use a sign chart, or again, a test point, to find the sign in each interval. When you have some of these polynomial inequalities, it's very time consuming when you're plugging things in. So I would actually recommend in this situation to use a sign chart and not to get a point. So now I have put the solution together based on the inequality given. So the solution will contain any region that makes the inequality true. The endpoints are included for a non-strict inequality, and then the endpoints are excluded for a strict inequality. So this is very important to understand. Again, when I say endpoints, I mean the critical values, or again, you can think about these as the real zeros that we use to create those intervals on the number line. All right, so we're just going to take a few moments and think about where that procedure comes from and why does it work. So I have here, since the graph of a polynomial function is continuous, so we know what that means. It means we can sketch the graph without picking up the pencil from the paper. So I have here no holes or breaks in the graph. So its sign is only going to change from positive to negative or negative to positive by first crossing through the x-axis where the function value is 0. So we should know on the x-axis that the y value or the function value is 0. So this means between consecutive real zeros, which correspond to x-intercepts on the graph, the sign of the polynomial function is either always positive when we are above the x-axis or always negative when we are below the x-axis. So this right here is what leads to our procedure. All right, so coming down to the graph, I'll give you a quick visual explanation of what I just read. So you have something like f of x equals the quantity x minus 2 times the quantity x plus 1 times the quantity x minus 0.5 times the quantity x minus 3. So if I said find the zeros for this polynomial function, we know that we could take this right here, set it equal to 0 and solve, or we could just write everything in the form of x minus k, where k is the 0. So in other words, this 0 would be 2. This one you'd have to change it over into minus a negative 1. So let me just arrow to that and just say this would be changed to x minus a negative 1. Just so this is clear. So the 0 will be negative 1. This one is x minus 0.5, so it's just 0.5. This one's x minus 3, so it's just 3. So you'd have a 0 of 2. So that corresponds to this x-intercept right here, which is 2, 0. You have a 0 of negative 1. That corresponds to this x-intercept, which is negative 1, 0. You have a 0 of 0.5, which corresponds to this x-intercept, which is 0.5, 0. And then you have a 0 of 3, which corresponds to this x-intercept, which is 3, 0. So what we said above was that basically the sign of this function, so when we think about the y value or the function value, so it can only change from positive to negative or negative to positive by first crossing through the x-axis. So in other words, going through an x-intercept. So if you can find the x-intercepts, then you know that you can create intervals, and those intervals can be used to test. So one interval would be anything less than negative 1. Another interval would be between negative 1 and 0.5. Another one would be between 0.5 and 2. Another one would be between 2 and 3. And then the last one would be anything greater than 3. Because I know in the interval where x is less than negative 1, you can see that it's always positive. Then between negative 1 and 0.5, it's always negative. Then between 0.5 and 2, it's always positive. Between 2 and 3, it's always negative. And then anything greater than 3, it's always positive. So all you have to do, once you've found your x-intercepts, you use those x values to set up your intervals. You just pick something for x in that interval, plug it in, and then if your function value is positive, then it's always positive in that interval. If it's negative, then it's always negative in that interval. So very quickly, if I asked you, just looking at the graph, not doing any kind of algebra or anything, let's say we had x minus 2, and then times x plus 1, and then times x minus 0.5, and then times x minus 3. If I asked you where is this less than 0, again, just look at the graph and you would say, what are the x values for which the y values are less than 0? In other words, what x values can I plug in over here on the left such that this right here, this left side, would be less than 0 and this inequality would be satisfied? Where you're looking at this part right here, where the function values or the y values are less than 0 because we're below the x-axis, and then this part right here. So in other words, if I wanted to solve this guy right here, I would just say that x is greater than -1 and less than 0.5, or again, you could put 1/2, or also right here. So x is greater than 2 and less than 3. All right, let's take a look at the first problem. So we're going to see that we have x minus 2, that quantity, times the quantity x plus 1, times the quantity x minus 0.5, times the quantity x minus 3. This is greater than 0. So this guy right here, again, this is your polynomial function that you're working with. And I'm giving you everything in factored form because it just makes it a little bit quicker. So this guy right here, the first thing is you would just replace this with equals. And you would solve this. So x minus 2, that quantity, times the quantity. I'm going to change this to x minus a -1, like we did before. And this would be x minus 0.5, and this would be x minus 3. So if it's in the form of x minus k, again, you don't have to use the zero product property. You could do that. You could say x minus 2 equals 0, solve that, then or x minus a -1, or you could do x plus 1 equals 0, solve that, so on and so forth, and just keep going. But if it's in the form of x minus k, just take the k as the 0. So the zeros here, the zeros, you would have 2, -1, you would have 0.5, and then 3. So the only mistake that I see people making is not rewriting stuff that's something like x plus 1. Remember, it's got to be x minus k. So if it's x plus 1, change it over to x minus a -1. So these right here, again, let me paste this in. If you think about the zeros, again, if they're real zeros, they correspond to x-intercepts on the graph. So I just have my x-axis here, just so we can see this. So your 0 of 2, again, you get an x-intercept of 2, 0. Your 0 of -1, you get an x-intercept of -1, 0. Your 0 of 0.5, you get an x-intercept of 0.5, 0. Then your 0 of 3, you get an x-intercept of 3, 0. So again, we're going to have an interval where x is less than -1. We're going to test there. We're going to have an interval between -1 and 0.5. We're going to test there. We're going to have an interval between 0.5 and 2. We're going to test there. We're going to have an interval between 2 and 3. We're going to test there. And then we're going to have an interval where we're greater than 3. So you have your intervals, anything less than -1, between -1 and 0.5, between 0.5 and 2, between 2 and 3, and then anything greater than 3. So if you look at this factor right here, x plus 1, we know that it would be positive. Again, you could just solve the inequality. Let me do this to the side. Something like x plus 1 is greater than 0. Subtract 1 away from each side. So this is true wherever x is greater than -1. So that's going to be for anything here, 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 or here. But in this one right here, where we're less than -1, it would be negative. Using a similar thought process, you could fill out the rest of this table. Okay, so this guy right here, this x minus 0.5, that factor, it would be negative here, and then positive here, here, and here. And then this x minus 2, that would be negative here, here, and here, and then positive here and here. And then x minus 3, that would be negative here, 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 and here, and then positive here. So setting this up is pretty quick. Again, if you want to do the plugging in method, that's fine. Sometimes it's faster, it just depends. But you're just going to look through and see, do I have an odd number of negative factors or do I have an even number of negative factors? Here you have 1, 2, 3, 4 odd negative factors. So 4 is an even number. So the result of this guy would be positive when these guys get multiplied together. Then this guy right here, you have 1, 2, 3 negative factors. That's an odd number. So this would be negative. Then here you have 2 negative factors. So that's a positive. And then here you have 1 negative factor. So that's a negative. And then here you have no negative factors, right? So it's all positive. So it's positive. So if we think about the intervals where this guy is going to be positive, it's anything that's less than -1, it's anything that's between 0.5 and 2, and then anything greater than 3. Let me come up here, a little bit easier to see. So I'm going to say that my solution is going to be x is anything where we're less than -1. Then I'll put or. We're going to have between 0.5 and 2. So x is greater than 0.5, or again, you can use 1/2, and less than 2. And then I'll put or again. We're going to have anything where x is greater than 3. So x is greater than 3. Let me go ahead and grab this, and I'll just paste this in. So this is one way to write it. A lot of times people like to write this in interval notation. So for interval notation, you're going to have coming from -infinity, going up to and excluding -1, and then you want to use a union symbol. So this one right here is going to be, again, everything's excluded here because we had a strict inequality. So between 0.5 and 2. So again, nothing's included, so you're using a parenthesis at each end. And then the union with, you can have anything that's greater than 3. So just like that. And then if you want to do this on the number line, let's see. We want anything that's less than -1. So again, I'm going to use a parenthesis there. If you want, you can also do the open circle like that. But this is what I've always used, so I'm just going to stick with that. and just shade everything to the left. And then you also have between 0.5 and 2. Let's shade that. And then you have anything that's greater than 3. So let's shade that. So that would be your answer. And let me paste this in. So we've already seen this. So if I'm looking again at the graph for confirmation, and I left you a Desmos link for everything so you can just look at it. We're saying that this guy right here is greater than 0, where x is less than -1. Yeah, that's true. Look at the function values here, or the y values. They're positive when x is less than -1. Then if you look between x values of 0.5 and 2, again, that's going to be this part right here. Again, we're above the x-axis, so the function values or the y values are positive. Then again, when x is greater than 3, so that's going to be right here. Again, your function values are going to be positive. All right, let's take a look at another example. So here we have 1/12 times the quantity 2x minus 5 times the quantity x minus 5 times the quantity x plus 4 is less than or equal to 0. The first thing I would do here is get rid of this 1/12. It's not going to change your answer. So 2x minus 5, that quantity, and then times the quantity x minus 5 times the quantity x plus 4, multiplying both sides by 12, that's not going to change the solution at all. So this right here, you can just say it's less than or equal to 0, and we're just going to work with this form right here. It's just a lot easier to do. Let me just put a little border here, like that. When we graph it, we'll graph the original one, but if you want to graph this on Desmos, you'll see the answer is exactly the same. So again, you can set this equal to 0, and so now I have this quantity 2x minus 5 times the quantity x minus 5 times the quantity x plus 4. And you could use the zero product property here. So again, you could set each one of these equal to 0 and you could solve. But again, I think it's easier just to put everything in the form of x minus k. This one's a problem because you have 2x minus 5. So you could just pull the 2 out. So 2x divided by 2 would be x. And then -5 divided by 2 would be -5 halves. So this is x minus 5 halves. So let me actually rewrite this one. So I'm going to change x plus 4 into x minus a -4, just so this is crystal clear. Don't want to lose anybody. And actually, let me change that over to that. So this is equal to 0. Okay, so I can just grab the zeros now. So it's going to be 5 halves, 5, and then -4. So let me write that out. So the zeros, that's going to be 5 halves. You're going to have 5, and then -4. So let me grab this and come down here. So all we really need to know are what are those x-intercepts going to be, or what are the x values for that, so that we can, again, set up those intervals on the number line and then test inside of each interval. So you have one x-intercept that's going to be -4, 0, again, because we have a 0 of -4. You have another one that's going to be 2.5, 0, because we have this 0 of 5 halves, which is 2.5. Then we have another one that's 5, 0, because we have a 0 of 5. So we're going to have an interval where x is less than -4. We're going to have one between -4 and 2.5, one between 2.5 and 5, and then one that's greater than 5. Now, I went ahead and set up the table. So we have these factors right here. Again, if you just want to plug something into this in each interval and see if it works, is it positive, is it negative? That's up to you. Sometimes that's faster, sometimes it's not. Again, it's just based on the problem. Again, you had that 1/12 out in front when we started. Remember, that's not really going to change anything because it's just a positive number that's multiplying all these factors right here. So again, you could just get rid of it. We multiplied both sides by 12. The answer will be the same. When we graph it, it'll look different, but the answer will be the same. So this guy right here, this x plus 4, would be negative here, positive, 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 because it would be positive for any x value where we're greater than -4. Then 2x minus 5, that would be negative here and here, and then positive here and here, because that would be positive for any x value that's greater than 2.5. Then x minus 5, that would be negative here, here, and here, and then positive here. That would be positive for any x value that's greater than 5. And then this guy right here, again, all you're doing is you're looking at, do I have an odd number of negative factors? Well, here it's 1, 2, 3, that's odd, so I'm going to get a negative. This is positive, negative, negative. That's an even number of negatives, so this is positive. This is positive, positive, negative. 1 is an odd number, so an odd number of negatives, you're going to get a negative. And then this is all positive here, so this would be positive. So what you can say is that for the less than or equal to scenario here, we would say that x is less than or equal to -4, then or you're going to have that x is greater than or equal to your 2.5 and less than or equal to 5. So this is what you want. Let me grab this. And again, if you want to do interval notation, so these are all going to be included because, again, we had a non-strict inequality. So here we would say coming from a negative infinity, going up to and including -4, and then the union with, you're going to have anything between 2.5 and 5, with both of those guys being included. Okay, so looking at the graph, let me fix this right here. You want to say, you can put a bracket at -4, or again, if you want to do a filled in circle like that, that works as well. I'm just normally using a bracket, so I want to stay consistent. So at -4, maybe that's a little bit too far to the left, so let's do it like that. So the other one would be between 2.5 and 5. I'll just shade all of that. Now let me grab this. All right, so coming down here, again, I'm using the original f of x equals 1/12 times the quantity 2x minus 5 times the quantity x minus 5 times the quantity x plus 4. I gave you a Desmos link. If you want to put your cursor right here and delete this right here, you'll see that the graph is going to change. It's a different function you're working with, but the solution would still be the same. So if you look at this, we're looking for where, again, this part right here is either 0 or less than 0. So you would have a solution at -4, 0, and then anything to the left in terms of the x value. So anything that's -4 or less, so x is less than or equal to -4. So that's this part right here. Then also, this would be true where x is greater than or equal to 2.5, there's 2.5 right there, and less than or equal to 5, there's 5 right there. So all of these values right here. All right, let's take a look at one final problem. So this one has a few things in it that I think are important to understand. So we have the quantity 2x squared plus 5x plus 4 times the quantity x minus 1 squared times the quantity x minus 2 is greater than 0. So first, let's just write this as 2x squared plus 5x plus 4. And then this right here, x minus 1 quantity squared. And this one right here is x minus 2. And let's set this equal to 0. So we know that we would have zeros in terms of real zeros. Let me put that here so I am more specific here. Let me put real zeros of 1. Now notice the multiplicity is 2. So that means when we get to our x-intercept at 1, 0, it's going to touch and turn around. Let me show you that real quick. I'm hoping you remember that from our lesson. Here's that x-intercept of 1, 0. Again, we're negative, negative, negative. We're going to touch and then turn around. Okay, because there is no sign change on this side to this side because of the squaring operation. The 2, 0, well, that one, the multiplicity is 1, so it just goes straight through. This side of it is negative, this side of it's positive. So again, we talked about that earlier. Let me go back. So the real zeros, we have 1, and then we're going to have 2. Now, what about this guy right here? Well, you should know that you can use something called the discriminant, and that is b squared minus 4ac. And you want to see, is that negative? If it is, again, that's the part under the square root on your quadratic formula that tells you you're going to have two non-real complex solutions. So this right here is your a, this is your b, and this is your c. So b squared minus 4ac, you want to see if that's negative. So b is 5. 5 squared is 25. And then a would be 2, and c would be 4. So 4 times 2 is 8. 8 times 4 is 32. So what is 25 minus 32? That is going to be -7. Because this guy does not have any real zeros involved, and I'm talking about this specifically right here, when you look at it, it's not going to have any x-intercepts. So this guy is either always positive or always negative. Let me come down. I'm just going to show you this with a graph. So this is f of x equals 2x squared plus 5x plus 4. Again, there are no real zeros for this, so you see that it does not touch the x-axis ever. So it's either always positive, so it's above the x-axis, or it's always negative, meaning it's below the x-axis. Here from the graph, you can see that it's always going to be positive. No matter what x value I pick and plug in, it's always positive. And all you have to do in this scenario is pick something, usually you just pick 0, plug it in, and see what you get. So here, if you plug in a 0, so f of 0, you would get, this is going to go away, this is going to go away, you just have 4. You can see you have this point right here, which is 0, 4. But that 4 right there is positive, so it tells me that this guy's always going to be positive. So just keep that in mind. When we come down to set up our intervals, again, the only things I'm going to worry about were the real zeros. So I had a real zero of 1, so I get 1, 0, and I had a real zero of 2, so I get 2, 0. But again, remember the behavior of this guy, the multiplicity of this was 2, so it's going to touch and turn around there, whereas this one, the multiplicity was 1, so it's going to cross through. So that's something you just want to keep in mind. You're still going to split this up into intervals, so anything less than 1, anything between 1 and 2, and then anything greater than 2. This 2x squared plus 5x plus 4, again, we know it's always going to be positive. It will never be 0, and it will never be negative. We saw that earlier. So I put positive, positive, positive. This x minus 1 quantity squared, again, that's either going to be 0 when x is 1. Again, that's at your x-intercept, so 1, 0. And it's going to be positive everywhere else because of the squaring operation. So positive, positive, positive. So really, this other factor of x minus 2 is going to determine everything. So if you have something like x minus 2 is greater than 0, add 2 to both sides of the inequality. That cancels, you get x is greater than 2. So x needs to be greater than 2 for this to be positive. So in this interval, it's negative, in this interval, it's negative, and then here, where we're greater than 2, it's positive. So if you look, you have positive, positive, negative, so that's going to give me a negative. Positive, positive, negative, that's going to give me a negative, and then positive, 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 that's going to give me a positive. We're really only going to say that the answer here is where x is greater than 2, and strictly greater than 2. Let me come down here and say that x is greater than 2. In interval notation, this is just 2 going out to positive infinity. Again, make sure that you use a parenthesis next to 2, it's not included. And so here, again, you could put an open circle, or I'm going to use a parenthesis there, and then just shade everything to the right like that. And again, just looking at this on the graph, because this 0 had a multiplicity of 2, it was even, it touches and turns around. So it's negative, negative, negative. It's going to go to 0 at an x value of 1. Then it's going to go back to negative, 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 negative. And it's not going to get to positive until we get past an x value of 2. So at an x value of 2, again, this guy is going to be 0. But anything to the right of 2 in terms of the x value, now we're finally going to have a function value that's positive because this is positive. So for anything there that x is greater than 2, we would have a function value that is positive, or you could say a y value that's positive. So not 2 itself, but anything greater than 2. So that's this piece of the graph right there. In this lesson, we want to talk about solving variation word problems. All right, so earlier on in the course, we talked about the slope-intercept form of the line. So that is the y equals mx plus b, where m is known as the slope of the line, and the y-intercept is going to occur at the point 0, b. So we would say that when b, so this guy right here, is 0, the y-intercept occurs at 0, 0, so that's the origin, and the line can be written as just y equals mx. Because again, if this is 0, this would be y equals mx plus 0. So you could just get rid of that. That's not going to do anything. So here we would say that y is a constant multiple of x. So for example, let's say you had something like y is equal to 2x. Well, y here is just going to be 2 times whatever you plug in for x. So if x is 5, y would be 10. If x was 20, y would be 40, so on and so forth. Now, when we talk about direct variation, and we're going to have different types of variation, but direct variation is the first one that you often come across. Direct variation occurs when one quantity is a constant multiple of the other. So a moment ago, we saw y is equal to 2x. So again, I plug in something for x, I multiply by 2, and I get my y. So y is twice whatever you plug in for x. If x is 5, y is 10. If x is 20, y is 40. If x is 100, y is 200, so on and so forth. So when this occurs, you could say y varies directly with x or is directly proportional to x if there exists a non-zero real number k such that y equals kx, where again, I put k is not equal to 0. So this right here, this k, which is 2 in this equation that I set up here, is going to be known as the constant of variation, or some books will call it the constant of proportionality. What I wrote here is y varies directly with x. Some books, just so this is clear, they're going to word this differently, so I don't want you to get lost. You might see y varies directly with x. This one's very common, so you might see y varies directly as x, means the same thing. You also might see y is directly proportional to x. Again, all of these have the same meaning. So depending on your textbook, you might get different wording. Okay, let's look at a simple example just to get things started. So we have that a flooring company earns $2 in profit for each rug sold. How much would they earn for 100 units, 200 units, and then 1,000 units sold? So this is just a typical plug and chug that you'll get at the beginning of the section. So first you're going to set up your model. So y equals 2x because it's 2 times whatever the number of units of rugs that they're going to sell. So x is just the number of rugs they're going to sell. Let me put here, and this would be units sold. So again, this is in terms of rugs. And this y right here, this is going to be the total profit. So this is your total profit. So I have here a restriction that x is greater than or equal to 0. In this section, they usually don't put restrictions in. Sometimes they do, but a lot of times they don't because it's pretty obvious that you're not going to be able to sell a negative number of units. So you really don't need to put that in there. You would make $0 in profit if you didn't sell any. And of course, you could sell any positive amount that you want up to a certain point. There's only so much demand. There's only so much material. So there would be a realistic cap on this as well. But for the purposes of this problem, we'll just say that x is greater than or equal to 0. So if we want to figure out how much they would earn for 100 units, you could change this over into function notation. You could say f of x is equal to 2x like this, and you could put the restriction if you want. So x is greater than or equal to 0, or leave it off. It's really up to you. So we would start with 100 units. So f of 100, very easy. This would just be 2 times 100, which of course is 200. And then you would want f of 200. So this is 2 times 200. And of course, that's just 400. And the last one would be f of 1,000. And so this is 2 times 1,000. And of course, that's just 2,000. So a very simple problem just to get things started. A lot of times in your book, they will show you a graph. So here's your units sold. That's going to be for the x-axis. The y-axis is going to be for the profit. Again, because I've restricted this to where x is greater than or equal to 0, we're going to start here at the origin. So if you don't sell any units, you're not going to make any money. So that's going to be the point which is 0, 0. No units sold, no money earned. Then we saw something like 100, 200. So you sell 100 units, you make $200. 200, 400. You sell 200 units, you make $400. And then we have 1,000, 2,000. You sell 1,000 units, you make $2,000. So for all the different variation problems we're going to see today, it's going to be the same basic procedure. So for solving a variation problem, first you're going to write out the variation equation. It's very easy to do once you get used to these problems. So you'll have a formula that you use in general for direct, inverse, joint, or combined. And then you're going to use substitution to find k. That's your constant variation. Once you know that, you're going to replace k in the equation. So in your model that you set up, and then you're going to find the remaining unknown values. So that's going to allow you to solve the problem. So really, these are just going to be the typical plug and chug problem. All right, let's take a look at the first problem. So this will be for direct variation. So we have that the number of gallons of water used when taking a shower varies directly with the time spent showering. So earlier today, Mary took a shower lasting 12 minutes, which used 25.2 gallons of water. How much water is used by Beth, who takes a shower that lasts 7 minutes? Okay, so for this one, the first thing you would do is just to set up your model. So what is the variation equation we would use here? This is direct variation because it says varies directly with, so we know it's direct variation. Now, you can use y equals kx if you want. You have to be careful with using this generic notation. If you do, I would label things, especially when you're first getting started. That way you don't make a mistake with what you're plugging in. Because for the y here, that's going to be the number of gallons of water used when taking a shower, and the x here would be the time spent showering, because y, again, varies directly with x. So you could change this up, and instead of y, you could make it more descriptive and use g for gallons of water. You can use whatever you want. Maybe you want to use w or something like that. And then instead of x, you could use t for time. And I think if you do this, it makes it a lot easier to plug in and remember what represents what. So I'm just going to keep this as the model. So again, the first thing is you're going to solve for k. So to do that, you could divide both sides of the equation by t. So you would say that k is equal to g over t. And then you just plug in the initial information. So it says earlier today, Mary took a shower lasting 12 minutes. So the time, you're just going to replace that with 12, which used 25.2 gallons of water. So you're going to replace the g with 25.2. So once you've done that, you're just going to punch this into the calculator, and I get 2.1. So what this tells me is that this shower head that they're using is going to flow at a constant rate of 2.1 gallons per minute. So I'm not going to worry about any units right now. I'm just going to plug this in for k. So I'm going to say, just update the model. So g is equal to 2.1, that's my constant variation, times my t. So in this situation here, it says how much water is used by Beth, who takes a shower that lasts 7 minutes. Well, all you have to do is plug in a 7 for the t right there. That's it, you're done. So g is equal to 2.1 times 7, which would be equal to 14.7. So what we would say here, or what we would conclude, when Beth takes a shower that's 7 minutes, she's going to use 14.7 gallons of water. So I'll just write out 14.7 gallons of water. And I think that's good enough for me. If you want to write out a full sentence, that's up to you. But this is how I would answer this. So I would just say 14.7 gallons of water. Again, that's what Beth is going to use when she takes the shower. That lasts 7 minutes. All right, so I'm just going to show you one other graph. You can make these on Desmos if you want on your own for the rest of them, but I think it's a little bit interesting to see how things look. It'll give you a visual idea of what's going on. So the x-axis here is the time in minutes, and the y-axis here is water in gallons. So we have the model y equals 2.1 times x. Again, just saying that y is always going to be 2.1 times whatever x is, because 2.1, that's the amount of gallons per minute that shower head is pushing through in terms of water. So we see here that we have a restriction. Again, you don't have to write it in this section. It is obvious to everyone that x has to be greater than or equal to 0. You cannot take a shower that has negative minutes involved. It's either going to be 0 minutes, where you would not use any water, so that would be the ordered pair 0, 0, or it's going to be some positive amount of minutes. And so something like Beth, who takes a shower that's 7 minutes, well, she's going to use 14.7 gallons of water. So that's that 0.7, 14.7. And then something like Mary, the original person that took the shower, she takes a 12-minute shower and she uses 25.2 gallons of water. All right, let's talk about partial variation now. So this is something that most textbooks don't actually cover. So I'm just going to give you a simple example so you know what it is, but it's very unlikely that you would actually see it on a test or get homework on it. You have something like y equals kx plus c, where k is not 0 and c is not 0. So if we relate this back to y equals mx plus b, well, here, this is a line that's not going to go through the origin because the b value here, which is is the y coordinate for your y-intercept, it occurs at 0, b, well, that's not going to be 0. So for example, you might have something like y equals 2x plus 5. Well, when I had y equals 2x, y was a constant multiple of x. It was 2 times whatever x is. But now you can't say that anymore because you have this plus 5 right here. So let's come down here, and I'm just going to give you a quick example of this. It's just as easy to figure out. So we have something like a local car rental company charges a daily fee, let me highlight that, of $125. Then we have plus a per mile fee. So Jason rents a car for 1 day and drives a total of 190 miles. The total rental charge before tax was $145.90. Find the rental charge before tax if Tom rents the same car for 1 day and drives 300 miles. Okay, so this one's fairly straightforward. What you have to realize is that if you're using a model, let's say it's y equals kx plus, let's just use c, there's a k that's a constant of variation, so that's not going to change. That's the per mile fee. In other words, this has to get multiplied by something in terms of x, where you're plugging in the amount of miles that's being driven over the course of that car rental period, whatever that is. So this is your constant of variation, but it deals with the per mile fee. This c out here is a constant, but it's not going to depend on how many miles that you drive. It's just a flat fee. So again, they charge a daily fee of $125. So you can just replace this c with 125 just to get things started. Now for this, again, the x, that's going to be how many miles that you're driving in terms of the rental, and then y, that's going to be the total rental charge before tax. So if we plug in the initial information, it says Jason rents a car for 1 day. So again, you're just getting a $125 fee and drives a total of 190 miles. We'll just plug in 190 there. Let me move this down. Let me put this as 190 times k. And then your y, that's the total rental charge before tax. That's going to be 145. 0.9. You can put 0.90 if you want. I'm just going to put 0.9. And essentially, we know how to solve a linear equation in one variable. It's very simple. We're going to subtract 125 away from each side of the equation. So let's go ahead and cancel this. And we're going to say 145.9 minus 125. That's going to be 20.9. And this equals 190k. So I'm going to divide both sides of the equation by 190. And of course, this is going to cancel, and you're going to get k is equal to, so 20.9 divided by 190, that's 0.11. So essentially, it's 11 cents per mile. So let me erase everything, and I'm just going to write that k is equal to 0.11, again, 11 cents per mile, and then just rewrite the model. So y is equal to, your k is 0.11, and then times whatever x is, we'll plug in a moment, and then plus, again, that daily fee is $125. Okay, so it asks us to find the rental charge before tax if Tom rents the same car for 1 day. So again, the fixed fee here is still 125 and drives 300 miles. So really, all we have to do is plug a 300 in there for x. So y equals 0.11 times 300 and then plus 125. So that would be equal to, so 0.11 times 300, that is 33. And so you'd have 33 plus 125, punch that into the calculator, and I get 158. When Tom rents the same car for 1 day and drives 300 miles, he's going to end up paying $158. Again, if you want to write out a sentence, you can. I'm just going to write out $158, and this is going to be my answer. All right, so we also have direct variation with powers. So let n be a positive real number. So that's going to be this guy right here, the exponent. So then y varies directly with the nth power of x if there exists a non-zero real number k such that y equals kx to the nth power. Okay, let me give you an example. So we have that the weight of a great white shark varies directly with the cube. So that means we're raising to the third power of its length. So we have weight here varies directly with the cube of its length. So a great white shark caught in the deep ocean was 25 feet in length and weighed 9,375 pounds. What is the weight of a baby shark that is 5 feet in length? So again, just start with your model. So in this case, you could put W for weight is equal to, you would have your K, your constant of variation, and then the cube of its length, so you can put L cubed. So I'm going to write my L like that so it doesn't get confused with a 1 or an I or something like that. And so basically you could set it up like this. Again, if you're more comfortable, you can use y equals kx cubed. You can do that as well. It's up to you. It's all personal preference. So you're just going to plug in the initial information. Again, if you want to solve for k before you do that, you can divide both sides by L cubed. So you can say k is equal to, you would have W over L cubed. Let me fix this and make it a little bit better. And so what are we given? We're given that a great white shark caught in the deep ocean was 25 feet in length. So this would be a 25 here, and that's going to be cubed. And it weighed 9,000 375 pounds. So let's punch this into the calculator, and I get 0.6. So let me erase this and just put 0.6. Again, you could just update the model. So your W, that's your weight, is equal to your K, your constant variation is 0.6, and then times whatever your L is, and that's going to be cubed. So I'm just going to write it like this. Let's get rid of that. I'll just write it like this, and we're going to plug in right now. So it says, what is the weight of a baby shark that is 5 feet in length? So just plug the 5 in right there for the L, that's the length. And 5 cubed, we know that's 125. So you could say that's 0.6 times 125. You could just punch that into the calculator, and I get 75. So the answer here, we're going to say, is 75 pounds. So again, if you want to make a little sentence, you can, but it's going to be 75 pounds in terms of the weight of a baby shark that is 5 feet in length. All right, now let's talk about inverse variation. So we have let n be a positive real number, so that's this exponent down here. Then y varies inversely with the nth power of x if there exists a non-zero real number k such that y equals k over x to the power of n. So typically, this is given as inverse variation as a power because we have this exponent involved. And when we start, we get something like y is equal to k over x, where n here would just be 1. So typically, you're going to see these as the easier problems. And then as you get deeper into the section, you'll get some that look like this. So really, it's the same process that you're going to use to solve those problems. Again, we saw y varies inversely with x, or actually up here it says inversely with the nth power of x. But again, if you're working on this model, it would just say y varies inversely with x. Coming down, you might also see y varies inversely as x or inversely as the nth power of x. You might also see y is inversely proportional to x or y is inversely proportional to the nth power of x, something like that. So let's look at a simple example. So we have the current in a simple electrical circuit varies inversely with the resistance. If the current is 25 amps when the resistance is 20 ohms, find the current if the resistance is 8 ohms. So again, it's a very easy problem. You can start with something like y equals k over x if you want, or again, you can change things. So we have current, you could use C for that if you want. So you can just use a C, you can use whatever letter you want, it doesn't matter. So it varies inversely with the resistance. So if you want to put an R down here for that, that's fine as well. So if the current is 25 amps, so I'm going to replace the C with 25. When the resistance is 20 ohms, so I'm going to replace the R with 20. And let's put the k up here. So what you want to do is use this to solve for k. Multiply both sides by 20. And so this right here is going to cancel. And so you're going to get 20 times 25. We could do 2 times 25, that's 50. Put a 0 in the end, that's 500. So we would say k is equal to 500. Okay, let me get rid of this, and we'll just replace that in the model. So C, that's for current, is equal to your k, your constant variation, that's 500. Over whatever R is. So in this part right here, it says find the current if the resistance, so that's going to be the R, is 8 ohms. So just replace this with 8 and just punch that into the calculator, and we're going to get 62.5. So let me come over here. I'll just answer this. So this is in terms of amps. So we're going to say it's 62.5, and then I'll write amps. Again, if you want to make a sentence, that's up to you. I'm just going to answer like this. All right, let's take a look at one where we have inverse variation as a power. So the loudness of a sound is inversely proportional to the square of the distance from the source of the sound. Amanda is 10 feet away from a pressure washer and experiences a sound level of 70 decibels. What is the sound level for Jamie, who is 40 feet away? Again, you can write out y equals k over x squared. Again, I'm getting x squared because it says square of the distance. Again, if you want to change the letters around, that's fine. For loudness, you can use an L. You could use a capital L or a lowercase l, whatever you want to do. For the distance, I think you would use d. So that would be d squared. So you can do it like this if you want. Let me actually make this easier and multiply both sides by d squared. So that would cancel this with this. And you would have that your k, your constant variation, is going to be equal to d squared, whatever that is, times your L. So then for the distance, again, Amanda is 10 feet away. Don't forget to square that, so it's going to be 10 squared. And then for the loudness, that's measured in decibels, it says the sound level is 70 decibels. So this is going to be 70 right here. You don't need a calculator for this, although you could use one. We know 10 squared is 100. So let me put down here equals 100 times 70. And of course, 1 times 7 is 7. And then you have 1, 2, 3 trailing zeros. So this is 1, 2, 3. So that's going to be 7,000 in terms of K, the constant of variation. Let me get rid of this, and I'm going to get rid of that. And we'll just put 7,000 up here in the numerator. And let me fix that. And you can get rid of this. And now all you have to do is plug in. So what is the sound level for Jamie, who is 40 feet away? Again, you would just plug in there and say this is 40. Don't forget to square that. And so let's just punch this into the calculator. And I get 4.375. This is going to be in terms of decibels. So I'll just write that down here. So 4.375. And then let me write out decibels. Again, if you want to make a sentence, that's up to you. I'm just going to stop here and say 4.375 decibels. That would be the sound level for Jamie, who's 40 feet away. All right, now let's talk about joint variation. So we have that y varies jointly with x and z if there exists some real number k such that y equals k x z. A common source of confusion when you see this wording here is this and people try to turn it into an addition, but really if you see y varies jointly with x and z, you're changing this into y equals kxz. Now you also might see this with powers involved. So in that case, you could write something like y equals, let's just go kx to the nth power, and then let's go z to the mth power. So you might see that in your textbook. All right, let's take a look at an example with joint variation. So we have here that the force of the wind blowing on a vertical surface varies jointly with the area of the surface and the square of the velocity. If a wind of 60 miles per hour exerts a force of 168.75 pounds on a surface of 0.75 square feet, how much force will a wind of 80 miles per hour place on a surface of 2 square feet? Okay, so let's start with a model. Again, for the force of the wind blowing on a vertical surface, you could use y, or in this case, I'd probably use F. So that's equal to, you have your K, that's the constant of variation. And then again, it says varies jointly with the area of the surface and the square of the velocity. So again, and does not imply addition here. So you're going to take A for area, or you could use X if you want. I'm just going to use A, and then I'm going to use V squared for the square of the velocity, and that's all going to be multiplied together. So the model here is F for the force of the wind blowing on a vertical surface is equal to K, that's the constant variation, times A, that's the area of the surface, times V squared, that's the square of the velocity. So if you want to solve this now for K, you would divide both sides of the equation by AV squared. So you'd have K is equal to, you'd have your F up here over AV squared. So the initial information, if you want to plug in and get K, if a wind of 60 miles per hour, that's getting plugged in for velocity. So this right here would be 60. And let's just square that, exerts a force of 168.75 pounds. So that's going to come up here. So 168.75 on a surface of 0.75 square feet. So we're plugging in 0.75 for the area. And let me make this a little bit longer. We'll key this into the calculator. Let me just fix the formatting here. So I get 0.0625. Okay, let me erase this, and I'll just slide this down over here. And again, all you have to do once you found K is just plug it in. So the updated model would be F is equal to 0.0625. Let me get rid of it. We don't need it anymore. And then times your A times your V squared. So in this part right here, it says how much force will a wind of 80 miles per hour. So for the velocity, you want 80 squared. Let me fix this 0 here. Place on a surface of 2 square feet. So for the A, you want a 2. So all we're going to do now is just plug this into the calculator, and I get 800. So this is going to be in terms of pounds for the answer. So let's say that it's going to be 800 pounds, like that. And again, if you want to make a sentence, you can, but this is going to be the force that this wind of 80 miles per hour is going to place on a surface that is 2 square feet. All right, for the last problem, we're going to see combined variation. So this is not something I can give you a model for, but essentially this scenario occurs when you have different types of variation that is mixed into the same problem. So going through this, we have the maximum safe load for a horizontal rectangular beam. So let me just highlight that right there. Varies jointly with the width of the beam and the square of the thickness of the beam, and inversely with its length. So let's stop for a moment. This is the hardest part for a combined variation problem. It's just setting up the model. So let's go step by step. We know that the first part says varies jointly. So if I had y varies jointly with x and z, that is y equals K times X times Z. So just like that. So just following that format here, you can use, let's say M for the maximum safe load. Again, use whatever letter you want. It doesn't matter. So I'm just going to put M. So that equals, again, if this varies jointly with the width of the beam and the square of the thickness of the beam, well, you're going to put your K here. That's the constant of variation. And then we're going to use a W for the width of that beam. And then let's use a T for the thickness of the beam. And this is the square of that. So let's go T squared. Okay, so that's the joint variation part. Let me get rid of this. Then we move on to the inverse variation part, which says and inversely with its length. So when you think about inverse variation, again, if Y varies inversely with X, that is Y equals K over X like that. So just translating that into the language of the problem, that just means that I'm going to keep what I have here. I already have the K, the constant of variation. It's varying inversely with its length. So I'm just going to put an L down in the denominator for length. So at this point, all you have to do is solve for K. Then you can plug in and find the value for K, then plug in and solve the problem. That's all we're doing. So for K, let me just write that over here. This would be equal to, you would multiply both sides by L over WT squared. So in other words, you would have ML over WT squared. So that would be your K. And let's read through this. We have if a beam that is 10 feet in length, so 10 feet in length, will support up to 600 pounds when the beam is 4 inches wide and 2 inches thick. What is the maximum safe load in a similar beam that is 12 feet in length, 6 inches wide, and 4 inches thick? Okay, so we're just going to plug in to find K. So in the first scenario, again, if a beam that is 10 feet in length, so the length is up here, so we're going to put 10 right there. And then it says, will support up to 600 pounds. Again, the M represents the maximum safe load for a horizontal rectangular beam. So that's going to go up here. This is my 600. And maybe I can move this down a little bit. And let me make this a little bit longer. Then it says when the beam is 4 inches wide. So the width is 4. Let's put that in down there. And 2 inches thick. So this would be a 2. And then don't forget to square that. So really, you could write this as 4 squared because 2 squared is 4. So it's going to end up being 16 in the denominator because 4 times 4 is 16. So this would be equal to 375. So that's my value for K. Let me get rid of this. And really, you can get rid of it from here. Let me slide this over. I think what I'm going to do is just write the K out in front. So 375 and then times, we'll just scooch this up like that. And basically at this point, we're just ready to plug in. So it says, what is the maximum safe load in a similar beam that is 12 feet in length? So again, the length is down here. So just plug in a 12. 6 inches wide. So the width is right here. So let's plug in a 6. And it says, and 4 inches thick. So you're going to plug in a 4 there. Don't forget to square that. So this is 4 squared. So this is equal to, again, lots of ways you can do it. I'm just going to key it into the calculator. And I get 3,000. So 3,000. And again, this is going to be in terms of pounds. So that's the maximum safe load for a horizontal rectangular beam. Again, when we're dealing with one that's 12 feet in length, 6 inches wide, and 4 inches thick. So let me write this with the units here so this is clear. The answer is going to be 3,000 pounds.